Hello everyone and welcome to today's lesson, which is on GCSE Chemistry. If you were here yesterday, welcome back. If not, thanks for all joining. I know it's really early on a Sunday, but we're going to go through quite a few things and hopefully help you learn them and be able to do better in your exams. So today we're going to be going through atom structure and bonding. So it's always the basis of chemistry is always what we're going through in the beginning. So hopefully this will help you when you're going on to the next lessons and in subsequent lessons to have the basics down. Okay. If I'm going too fast or too slow, please do let me know and I can slow down, just put it down in the chat. So just a little bit about me. My name is Tamkin. I'm a doctor. I work in North West London. Fun fact about me is I'm actually working in the same hospital that I was born in. And I did chemistry at GCSE level and also at A level, both to AS and A2. And I've been teaching for many, many years. So as soon as I was in A levels, I was teaching and I continued teaching throughout medical school and I'm still teaching now. So today we're going to start with structure of atoms, which is, like I said, the basis of all chemistry. And then we're going to go through the periodic table and then chemical bonding. Throughout this, we will have loads of questions just to make sure you're all awake and to keep you on your toes a bit. So do be prepared to answer the questions. They'll all be done on the Zoom poll. And then we have some exam questions as well, scattered in there as well to show you how we apply what we're learning to your exam and make sure you get those marks. We will have a few breaks in between as well, so that you can get up, have a walk around, have a cup of tea, grab a snack, and between 12 and 12:30, there'll be a longer break, so you can have some lunch if you want. But again, feel free to eat while you're in the lesson as well. You don't really need anything for this. If you want, you can have a piece of pen and paper just to take some notes if there's something I say that's not on the slide. But we will be sending you a recording of this with the presentation and all the questions we go through as well. So don't worry, you do not have to write everything down. It's probably better that you're just listening because that's how you'll remember it more. So if you were here yesterday, then you will know how it works. If you're new, then I'll just go through it very quickly. So we go through loads of different questions. So we will teach something and then we'll try to quiz you on it as we go through to make sure that you've understood it. And that way it gives us an idea if we need to go through something again as well. Like I said, we'll have actual exam questions as well that we'll go through. We have one of my colleagues on the chat as well. If you look for Ask Ace on the chat function, you can ask her any questions throughout. So she's sitting there to answer your question straight away. So if there's something that I've said that you're not sure about or you want some clarification, please do ask Ace and she'll answer you straight away. Throughout, I give you some top tips and some fun facts just to help you remember things. And like I said, this will be recorded. So just to reassure you, I'm sure if you were here yesterday, you know that anytime you answer a question I ask you, it comes only to me, so only I can see it. So please just answer. If you're not sure, if you think your answer might be wrong, it doesn't matter. Just put it in the chat anyway, because only I can see it. No one else can see the answers. So it's all, just for your learning. So if I do ask you a question, just please do get involved. It's the best way for you to learn as well. So the things that we're going to go through today. So as I mentioned, firstly, the basics and structures of atoms. Oh, let me just put my pen back on. Structures of atoms, and then we're going to go through the periodic table, mixtures and compounds, and then a bit of chemical bonding at the end. Okay, so it might seem like quite a lot, but actually you'll see that they all flow into each other quite nicely, so it should be okay. But like I said, if anyone's not with it or finding it a bit too fast or too slow, let Ask Ace know. You can even write in the chat to me and we can then adjust it. Okay, so I do want it to be interactive, so I want you guys to help me out here and help each other. So the first thing we're going to go through is the structure of an atom. Who knows what is an atom? What does it mean by atom? Who knows what an atom is? Tell me what you think and I'll write something else. Like I said, no one else can see your answers, so see what you think. So someone said smallest part of an element, well done. So you know what an element is. So anything else, what is an atom? So we've got a bit of a clue here for you here. So this little picture is an atom itself. Anyone know what else can you tell? Perfect, someone said atoms can be positive, negative, and neutral. So we'll go on to that. So atoms contain, it contains protons and neutrons, someone said. What else does it contain? We have something else in this way. So you have two things here. You have three little balls, electrons, perfect. Everything is made of atoms. Exactly. So everything is made of atoms. So atoms are made of elements. So sorry, atoms make up elements, and the smallest things of an element that can exist. Well done. So you know the basics. So atoms are the smallest part of an element that can exist. So if you ever need to have a definition of an atom, it's the smallest part of an element that can exist. Okay. So as someone said, they are made up of protons, neutrons, and electrons. Now put these in 3 different colors. You can tell me why. What's the significance? Why are they all different? So what can you tell me about protons? And the clue is in the first letter P. Someone said their charge. Perfect. So what is the charge of a proton? Well, wow, everyone's going crazy with positive. Well done. And that's the easiest way to remember it. So protons are positive, okay? Now, what about neutrons? Okay, this is a bit difficult because it doesn't go with a letter. Neutrons are, so remember, neutrons are neutral. Perfect. And then that leaves us with electrons. So we have something positive, something neutral. So what must the last one be? Perfect, negative. So if you remember that P and P, so protons are positive, neutrons are neutral, then you remember that electrons must be negative, okay? Excellent. So that's the main thing to remember, okay? So if you remember this, this is the basic of everything that happens in the rest of this presentation, okay? So you need to remember about positive charge, negative charge, and neutral charges, okay? So just to make sure you're all listening, we're going to do a quick poll. What are atom made up of? And if anyone gets this wrong, we're going to go back to the beginning. So you have to all make sure you get it right. I'm joking, we won't. Okay, this is all very reassuring for me. Okay. So I'm going to go ahead and assume that the person who clicked B, it was a clicking error, not that they thought it was B, but actually it's not wrong because they do have protons and electrons. But anyway, I'm glad that you all realized that atoms are made up of protons, neutrons, and electrons, okay? Now, just to make sure, again, you're still on track, we're going to do again. So have a quick think and tell me, protons have what? Again, well done. So most of you got that right. Well, nearly all of you got that right, and that protons have a positive charge. Remember P and P, protons positive. Okay. And as you did the last one, what do electrons have? So electrons, so protons are positive, we said, neutrons are neutral. So what that leaves us with is electrons which have a negative charge, okay? So again, most of you got that right, well done. So that's good. So just to reiterate for the people that weren't so sure, protons are positive, electrons are negative, and neutrons have no charge. They are neutral, okay? So neutral and no charge is the same thing. Okay, so now that's reassuring to me that we can move on, because that's the main thing to remember for this one. So we know that an atom has protons, neutrons, and electrons, but we need to know, where are they located? So this actually, this diagram tells you exactly where they're located. So you know that you have in this bit here, the circle bit here, what's this bit here called? It's labeled for you already actually, so it's called the nucleus. So remember yesterday in biology, you were going through the nucleus of cells. Actually, in chemistry, you have the same thing. So actually that should help you remember. So you have the nucleus, which is the central bit, and that contains protons and neutrons, okay? So this is important to know what's in the nucleus, okay? So that means that electrons, they're not in the nucleus. Now, what does that mean for these electrons? Are they just stuck in these bits here? What do they do? They orbit, exactly. So they orbit on shells. So these things here are called shells. Okay, these things here. So these lines actually are non-existent lines. It just shows you that the electron that you see here is constantly circling these shells. So these electrons are not stable, they're constantly moving. So if you remember that first picture on that first page, I'll just go back to show you. So this is how they're moving. Can you see here? They're constantly turning. So these lines are not really there. They just show you how they're moving. Okay, but the important thing is to know when you're talking about atoms, you want to know one of the things that are important in them is how much they weigh and what the mass is. Okay, so does anyone know with a proton, what's the relative mass? Now, when we say mass, we're not talking necessarily about kilograms, grams, and things. We just talk about the number relative. Okay, well done. Everyone's saying 1. Okay, and we've done this to death now. What's the charge on a proton? +1. And where is it located? In the nucleus. Okay, perfect. So we know if you ever get a table like this, which you will do in your exams, it always comes up to very easy marks. Protons have a mass of 1. They're 1 plus charge, and they're in the nucleus. Okay, so something you're going to remember that protons and neutrons are in the nucleus, and electrons are running around in the shells. Okay, how about neutrons? What's the mass of a neutron? Who knows? So everyone's saying 1. And what's the charge on a neutron? Perfect, 0 charge. 0 charge. Okay, so neutrons are neutral. Okay, so don't get confused with neutrons thinking they're negative. Neutrons are neutral. Okay, and where are the neutrons located? In the nucleus. Perfect. Okay, and now finally we have electrons. So who knows what's the mass of an electron? Perfect. So everyone's saying 0, 0, 0. So the mass of an electron is basically something, a very, very small number, like 0.00005. So tiny, tiny number. Okay. So you basically just write very small, or you can write 0. Okay. It won't be wrong. Someone's actually written 1 over 1,860. So I'm going to go ahead and assume that's right, but I never learned that. So don't worry, you don't have to ever learn that. What's the charge on an electron? Perfect, minus. So -1 and +1 is the same thing, okay? And where is the location of the electrons? In the shells, perfect. Okay, so this is important. You realize why it's important later when it comes to things like bonding, okay? So we know that protons are massive +1, neutrons are massive +1 as well, and electrons are so small we don't even count them in the mass, okay? Now, that's important because what that means is that the mass of the atom comes from these two, okay? You can have 100 electrons, it won't make a difference to the mass, really, okay? Maybe a very, very tiny amount. But if you change the number of protons and neutrons, it will make a difference, okay? So that's why it's important to know. And similarly, if you have more protons than electrons, you end up getting a positive charge. If you have more electrons than protons, you end up getting more negative charge. Okay, so now we're going to look at this example. So anyone know what element this is? You don't need to know what it is, but this would be interesting to see who knows what this is. Li, this one, perfect, lithium. Okay, well done, guys. So this is a lithium atom. Now it's got 2 numbers here, 1 up there and 1 over here. Who knows what these numbers are? So let's start with a bigger number first. What's this number? So a few of you say, so we're talking about the bigger number. So we're getting a combination of atomic number and mass number. So only one of you are correct. Well, only one group is correct. Okay, so the actual answer is that this bigger number is the mass number. Okay, and this smaller number is what you're calling the atomic number. So what does this mean? Okay, what do we mean by mass number and atomic number? Who knows? What does the mass number equal? So we know this is the mass number. Well, what do we say the mass of the atom comes from? So we said that there's only 2 things out of the 3 in an atom that give you the weight of the atom, okay? So we already know electrons do not contribute because they basically weigh nothing. So from there, we know straight away that actually it must be the neutrons and the protons that give you the mass, okay? Mass is another word for like the weight of it, okay? So we know that the only way you can get the mass of an atom, is adding the neutrons and protons, okay? It doesn't matter how many electrons it's got, it's not gonna make a difference, okay? So then who knows what this number is, okay? What's the smaller number? Brilliant, so you're all saying the protons. So the atomic number is what we call the number of protons, okay? And that's the smallest number, okay? Sometimes they're written not necessarily like this. You might get the 7 up here and the 3 here. You might even get the 3 here and the 7 here. It doesn't matter what the order is. The bigger number is always the mass number, okay? Because there's no way you can have 7 protons and the mass be 3. Does that make sense? It always has to be, the bigger number is the mass number. Now, the way I remember it, which I'll go on to tell you, is that the mass number is the bigger number. Mass is massive, okay? The mass is massive, which is the bigger number, okay? So if you remember, the mass number is the weight of the atom, and we know the weight comes from only protons and neutrons. And therefore, the mass number in an element is the number of protons and the number of neutrons, okay? And the atomic number is just the number of protons, okay? So atomic number is just how they're ordered in the periodic table, and that's why they go by atomic number. It just tells you the number of protons, okay? And that helps in other ways, which we'll go through. So what you can tell right now is that if you have a mass number of 7 and a proton number of 3, then you know that the number of neutrons must be 4, because that's how many you need to add to get from 3 to 7. Does that make sense? So if you know that the proton number plus the neutron number equals 7, and you know that the proton number is 3, and the neutron number you're not sure about equals 7, then this is a little bit of maths for you, but it's thankfully quite simple maths, that you know that this number must be 4. Does that make sense? Yes, great. Okay, so that's important to remember, because you'll often get questions asking you, what is the, this is the number of neutrons, what's the number of protons, for example, or this is the mass number, what's the number of neutrons? Okay, very, very common question to be asked. Okay, but the main thing to remember, the mass number is massive. Okay, I mean, obviously 7 is not massive, but compared to the 3, it's the bigger number. Okay, and this is just an example on a lithium ion atom, sorry. Every single number in the periodic table, sorry, every single element in the periodic table will have these 2 numbers, okay? Sometimes they're very specific and they'll have they'll have like 7.000 to account for the electron, okay? The other thing that you can learn from this usually is the number of electrons. So we know that atoms don't have an overall charge, okay? Atoms are overall neutral, okay? They're not positive and they're not negative when they're atoms. So if they have 3 protons, they must also have 3 electrons, okay? And the reason for that is if they had 3 plus charges and 4 electrons, then overall the charge will be -1, okay? So straight away you can see from just these 2 numbers, you know exactly how many protons, how many electrons, and how many neutrons. Does that all make sense and how you can calculate it? So if I were to ask you any of these elements, you will be able to get it right, because I will be asking you. Perfect. Okay, so just like I said, I'll be asking you, we're going to go for the first question. So take your time. I've done these so you don't necessarily need a pen and paper or a calculator, but you can use one. I'll just give you a clue in that this equals 201 minus 80, and this is 201 plus 80, okay? So what is the mass number for this? And this is actually mercury elements, okay? So Hg is mercury, don't worry about that. Okay, we've got a few more left to answer, and then we're going to show you what everyone thought. Perfect. Okay, so well done. I think most of you, almost all of you got that right. So I think I confused maybe saying massive. The mass number in this element was always going to be the biggest number, okay? So without even looking at any of the options, you can tell straight away the biggest number is 201, and therefore the mass number must be 201, okay? Don't let these things confuse you, okay? The mass and atomic number is always on the element, okay? So you can't usually get elements numbers from adding or subtracting when you're looking for the mass or atomic number, okay? Just remember the mass number and the atomic number are given to you. You do not need to do any calculations to calculate those 2. Okay, and remember we said that the atomic number is also the number of protons. Okay, we'll try another one now. So have a think of this one. What is the number of protons? So remember, what's the other word for number of protons? And you can calculate what this is. Well done. Okay, so again, very good. Majority of you, well, almost all of you got this one correct. So remember, the proton number is also known as the atomic number. And so atomic number and mass number are the two things that are given to you straight away. No calculations needed to calculate those two, okay? So this is number of protons. It's also the atomic number, okay? So remember we said the mass comes from protons and neutrons. And normally the number of protons is the same as the number of electrons because otherwise it would have a charge, okay? So remember the mass of an atom only comes from protons and neutrons, okay? We're going to try one more. So what is the number of neutrons in this? So again, I'll tell you this is 201 minus 80, and this is 201 plus 80. So we want the number of neutrons. Perfect. Well done, everyone. So much better. So I'm hoping that's all now made sense a bit more. So you can see all correctly identified C. So just to go over this example, so we know that the number of the bigger number, the massive number, the mass number is protons plus neutrons. This is just the protons and also equals electrons. And then in order to calculate the number of neutrons, we know that you do the mass number minus the proton number, okay? And you get this. Hope that will make sense, okay? You can ask if you're not sure. So then we have a little bit, something that complicates things a little bit, and that's called isotope. Does anyone know what isotope is and what it means? I don't know what an isotope is. Okay, so a few of you know, do you want to say an example of what an isotope is? Perfect, so someone has said same atomic number, but different mass number. Okay, so what does that mean? So remember we said atomic number equals number of protons, okay? So straight away, we know that an isotope will have the same number of protons, but it has a different mass number. So what makes up the mass of an atom? Protons plus neutrons. So if it's got the same number of protons, but a different mass number, it means that the neutrons must be different, okay? So I'll explain what that means to you here. So you can have an atom which has got the same number of protons. So for example, like that lithium, it's still got 3 protons, but it's not, instead of having 4 neutrons, it's got 6. Instead of having 4 neutrons, it's got 7, okay? So as I said, they have the same atomic number. I remember atomic number is number of protons, but they have a different mass number. So I'm going to show you how they present. So remember that we saw that lithium with the 7 and the 3. So this is similar. This is a carbon atom, okay? So we have 3 what we call isotopes. So this is going to involve a bit of calculation from you guys again now. So already straight away, we know that 12 is the mass number because it's a massive number. So 12 equals the number of protons plus neutrons, okay? So just by looking at this and having to do no calculations, you should all be able to tell me how many protons are in this carbon atom. Brilliant, everyone's saying 6. And how many electrons are in this carbon atom? Because it's neutral? 6, excellent, okay? So remember, the protons and electrons in an atom are always the same. Now, how many neutrons must be in this atom? If you've got 6 protons and a mass number of 12. Exactly. So 6, okay? So you have to have 6, because 6 to get to 12, you need to add 6. So if you have 6 protons, you need to add 6 to get to 12. I hope that makes sense. Okay, we'll try it with this one now, which is a little bit more tricky. So with this isotope, you have a mass of 13 and a proton number of 6. So already you know the proton number is 6, and the number of electrons is also 6. So remember, electrons don't change with isotopes, and neither do protons, okay? So already, even for this one, we know proton number is 6, electron number is 6. The difference is these numbers. So how many neutrons is there in this isotope where you need to go from 6 to 13? 7, excellent, okay? So you can see 7. And then from this one, to go from 6 to 14, what do you have to add? Perfect, 8, okay? Does that make sense what an isotope is? So an isotope will weigh differently, it'll have a different mass, so that's why the mass number is different, but it has the same number of protons. This bottom number here, which is the proton number or atomic number, has not changed at all. Does that make sense? Yes? Brilliant, thank you. For saying yes. Now, the important thing to note is that the chemical properties of all of these 3 carbon atoms are the same, okay? And that's because neutrons, other than adding weight or reducing weight, doesn't really make much difference to the atom. It just helps to stabilize it by giving it a bit of weight, okay? So whether this is 12, 13, 14, 20, 100, 500, it's not gonna make that much difference to its chemical properties. The things that make a difference are the protons and electrons, okay? So key thing to remember, the only thing that will affect the chemical properties of an atom is the number of protons and importantly, the number of electrons, okay? You can have 100 neutrons, it's not gonna make a difference because they don't add a charge, they're just neutral. All they do is add weight. So, just to test you a little bit, so the charge of the atom here is neutral. What is the charge of its isotope? I think we maybe tricked, it's a bit of a tough question. We'll wait for a few more people to answer. We're getting very mixed answers and I'll show you once we release the poll. Okay, so I'm glad I did this question. So let's show you what everyone thought. So as you can see, we've got a bit of a mixed bag, okay? So there's a mix between A and C and a few people thought B. Okay, so the answer to this question is actually neutral, okay? Now remember, just because this has got a higher mass number than this one, the only difference is the number of neutrons, okay? In order for and neutrons are neutral, or they have a 0 charge, okay? The only way this can become positive is if you add a proton, and the only way it can become negative is if you add an electron, or vice versa, remove an electron or remove a proton, okay? When you have an isotope, you're adding 1 neutron. So you're adding 0 charge. So if you're adding 0, you're not changing the charge, okay? So even though this number is getting bigger, the only thing that's changing is the neutron is being added, okay? You're not adding any positive or negative charge. You're not removing any positive or negative charge. So it will remain neutral, okay? So isotopes are always neutral, okay? The only thing that, remember, the chemical property is always the same. So it doesn't matter if this number is 12 or 13 or 22, it's not going to change the charge. It will still be neutral. Okay, important to remember, isotopes do not change charge, okay? And we're going to go into what charged atoms are later. So remember, an isotope is always neutral. So we have isotopes. So how do you know with this, when you have a bit of carbon in your hand, how do you know that, I don't have a mass of, I don't have 40 neutrons in this one and 20 in that one, and how does it make a difference? So, when we have a periodic table, we have the mass written, that lithium is 7, but actually, what if half of the atoms of lithium in that element are actually a higher mass because they have more neutrons? So in order to combat that and try to find out, actually, we might have some carbons with 12, some with 13, some with 14 as the mass number. What we want to do is find what the average is. So if we have an element, a big piece of carbon, how do we know what the relative, the average mass of that is, given that we may have some with a higher mass because they've got more neutrons, some with a lower mass because they may have low neutrons. And the way we do that is by looking at something called the relative atomic mass, which is basically just the average mass, okay? So this will take into account the fact that for those carbon atoms, you may have some with more neutrons and some with less neutrons, okay? I mean, they're never going to be so far out, like I've been saying, you're never going to get one with 300 neutrons and one with 20 neutrons. It won't be that different, okay? So there's a way we can calculate it. So we know that they have the same atomic number and a different mass number. So we can calculate the relative atomic mass by looking at the total mass of all the atoms of the element and dividing by the total number of atoms of that element. So this might seem a bit confusing, but what it means is that if you have, one carbon with 12, one with 13, one with 14, you just add those together and divided by the total number. So we're going to do an example, okay? And I want you to get a pen and paper and try this with me, and I'm going to talk through exactly how you do it, okay? So we have 75% with a mass number of 35 and 25% with a mass number of 37, okay? So as you can see, they're not that different, 35 and 37, they're quite close to each other. So because it's a percentage, we know it's out of 100, okay? We have a total of 100, but we can calculate that together. So we do 75% have a mass of 35. So we literally just multiply these two numbers together and you add it to the 25%, that's got a number of 37, okay? And then we know the total number that we have so as a percentage is 75 plus 25, okay? And you get a calculator for this, and it will tell you that when you multiply these two and add it to these two multiplied, it will give you the number 3550 divided by 100. Does that all make sense? So what you just do is multiply the two numbers, 75 by the number of the mass, 25% times the number of mass, and divide it by the total, which is 75 plus 25, or 100, okay? And that will give you the relative atomic mass of 35.5, okay? Was someone saying that Ask Ace doesn't work? I'll just get ahead to double check that. If you, as soon as you try to message her again, it should work now. Sorry, guys. So if you can see, this actually makes a bit of sense why it's 35. So we know that the majority of them are at a number 35 and a few of them are 37. So it's going to be between 35 to 37, the number, okay? And because the majority of them are 35, the number will be closer to 35, but just a bit higher than 35. This might seem like quite a lot, but we'll go through more examples in your question packs. And actually, if you do have any questions, we will see if we can send you some more of these. But it's basically multiplying the number of the atom together, adding them, and then dividing it by the total number, which you know is 75 plus 25. Okay, so just another quick question. To make sure you're all up to date. What is the definition of an isotope? I'm seeing some good answers. This is very reassuring. Perfect. Okay, so everyone now knows that isotopes of an element have the same number of protons but a different number of neutrons, okay? And that means that the overall charge does not change. Okay, so we know that all these atoms have protons, neutrons, and electrons, and we know that the protons and neutrons carry the mass and they're in the middle in the nucleus, okay? And we know that the electrons orbit in these shells around the electron. But the important thing to know is how do they orbit? Is it a complete random order? They go together, they separate. You know, if you have loads of electrons, how are they in this atomic structure? And this gives you a bit of a clue. So it can tell you, so this is a calcium atom, and you can see these crosses are the electrons, okay? So just by looking at this, you can see how many electrons are in this calcium atom, okay? But there's a specific way in which the calcium atom carries those electrons, okay? And we know they're in shells, so you can see 1, 2, 3, there's 4 shells. But actually the electrons actually take a very, very specific arrangement in these shells. And a few people have already mentioned what the arrangement is. So who knows how they arrange themselves? And you can actually see already in this first shell, you only have 2 electrons. So that means that the first energy shell will always carry 2 electrons in the first shell. Okay, so this is actually true for every single atom and element in the periodic table, okay? The first shell will always have 2. Now, how many shells can you see in the second? And luckily for you, they've come in pairs, so it's easier to count. 8, exactly. So you have 8 in the second shell. And how many in the third shell? Perfect. Well done. You guys all know exactly what you're doing. So 8 in the second and third shell as well. So this is important because this is exactly how electrons arrange in all atoms, okay? So you think it's specific for this calcium, but actually no. First thing to notice is that the electrons always occupy the lowest available energy level. And that lowest available energy level is actually this first shell, because it's closest to the protons and neutrons, it's closest to the nucleus, and that's where they want to go first. And in this first shell, you'll only ever get up to 2 electrons. Now I say up to 2 because you can get some elements which only have 1. There's only 1. There's an element which only has 1 electron. And if you have 1 electron, it will go into this lowest energy level in the first shell, okay? After this, you then get the second shell, which can hold 8 electrons, and again, up to 8. So you may have some elements which don't have enough to fill up 8, but they will fill up to 8. And the third shell, again, 8. Okay, so that's important for you to remember. Okay, so our top tip is electrons will always follow the 288 format. Okay, normally you don't need to know more than this, more than the third shell. Okay, or if you did, they will tell you exactly how many electrons in there. So does that make sense? The most important thing to remember is electrons follow the 288 structure. So you can look at it like a diagram like here. You can also just write, so for example, here we know it's 2 in the first shell, 8 in the second shell, 8 in the third shell, and then 2 in the fourth shell. So this will be written as 2, 8, 8, 2. Okay. Now, the reason that you want this 288 formation is because this is the structures of what we call the noble gases. Okay. And the noble gases is one of the elements right at the end of the periodic table, which all fill the 288 rule. So all of them have either 2, 8, or 8 electrons in the outer shell, okay? And that is like the ideal. Everyone wants to be like that, okay? So well done. Some people are actually talking to me about some of the ions, ion bonding. Well done, excellent. So just remember, all the atoms in the periodic table want to be with this, like these noble gases. They want to be like, you know, have a full outer shell. They want to have 2, 8, and 8, and nothing else. Okay. So having these extra, this 2 at the end is not very good for them. They don't like this. They don't like having these extra electrons hanging about when they want to have a full outer shell and make that 8. Okay. So if you remember that, all of the atoms in the periodic table want to have the noble gas structure of 288, then this will make it very easy for you to understand why these are reactive and how they bond. Okay, so again, we can see it's got 2, 8, 8, and then it's got this extra 2 at the end, at the highest energy level. So we go from lowest energy level to highest energy level at the outside. Okay, and remember in here, we have protons and neutrons, and these are all the electrons. So we're going to do some electron structure writing. So we have the diagrams, and I want you guys to tell me what it looks like when you're writing it, okay? So this one has got 2 electrons, so it's simply 2. So I'll do the easy one for you. Now I want someone to tell me what is the electron structure of this one. So you have 9 electrons. How are they going to be organized? So key tip, always start with 2, okay? You always have to have 2 in the lowest energy level. So as long as you've got more than 2 electrons, it's always 2. And then you can have up to 8 in the next one, but you've only got, if you do 9 minus 2, you have 7 electrons left. So you must have 7. You can have a maximum of 8. Does that make sense why that's 7? Okay, so now you do 7 plus 2 and you get 9. Okay, but you have to have 2 in the first shell and then 7. And now how about this one? So again, we know we start with 2. So now we have 11 electrons left. And then we know the next one you can have 8. So then how many electrons do you have left? 3. So it must be 283. Does this make sense? Because I don't want to go too fast if people don't get it. So you should remember, you always have 2, 8, and 8 is your ideal. You won't always have 8, okay? So let's do 19. So we know we start with 2. So the way I like to do it is, so we know we start with 2. So we remove that, make that 17 electrons. Then we know you can get 8. So you get 9 electrons. And then you have another 8 you can fill in, and then that leaves you with 1. Perfect. Okay, good. You're all getting it right, so that's all really reassuring. Okay. So just remember, if everyone wants to have the 288 structure, and then any electrons you have left at the end, you just add it on. Okay. So time for you guys to try now. How many electrons are in the outer shell of an atom with 12 electrons. Okay, and remember the configuration you ideally want, which is the 288. So you have 12 electrons. So we're asking how many in the outer shell. So just to give you a bit of percentage, so you know you want 288. So what would be, this is what you ideally want, and you have 12 electrons. So how can you make 288 with 12? Well done. So perfect. So the answer is actually 2. So just to explain how that works, so if you have 12 electrons, remember, so you know you're going to have 2 in the first one, always, so that leaves you with 10 electrons, and then you want 8 in the next one, so that leaves you with 2 electrons, then you have to have 2, okay? So as soon as you can make 2 and 8, you know whatever's left over will give you that. Okay, so just before we take our break, I'm going to go through very quickly a bit of history that you all have to know, unfortunately. Well, maybe not unfortunately if you like history. So one of the ways that they initially thought, so we know now that atoms are a nucleus with protons and neutrons with the surrounding electrons, but actually back in the early 1800s, when they first discovered atoms and what atoms were, they actually thought it looked like this, that you had this ball of positive charge and these electrons kind of running through it. Okay, that's what they thought it was. And to them, this made sense because, you know, who would have thought that electrons are orbiting without knowing what it is? But actually, later on, someone discovered it's not like this. And this was Ernest Rutherford. And what he did is he had a beam of alpha particles. And obviously back in those days, where earlier days, they may not have had this technology. And he got this beam of energy and was firing it at these pieces of atoms. And what he found is that some of it was going straight through, but some of it was being deflected. Now, what that meant is that it must be something where some of it is being deflected out, but the rest of them, which is where the electrons are, is able to let things go past through it. So this is the whole atom. And you have the electrons orbiting, and that allows things to go through. But the protons and neutrons in the middle is not letting things go through. So this made them then rethink the whole model. So we've gone from the plum pudding model, which is where you have, it's like a pudding, you have the little electrons there, to what we have now, which is the nuclear model, which is where you have a center of protons and electrons, sorry, protons and neutrons, very important to distinct that, and then the electrons surrounding it in orbit and moving, okay? And that's why the tiny bits that bounced back was just hitting the tiny central nucleus, whereas the rest of it was actually allowing things to go through, okay? So something you just need to know about how things were developed. And that's perfect. And someone's actually written, Rutherford alpha particles find got exactly gold sheet of foil and showed that there was a nucleus. So that's something important to remember. So I think what we'll do is we'll just do these few questions, which are actual exam questions. We'll do them together, and then we're going to have a break in 2 minutes. So this should be very, very easy for you guys because we've gone through it. What is the mass of a proton? 1. Proton is 1, and protons are found in, and these two are found in the nucleus. Remember, this is where the mass comes from. And what's very, very small? Electron. Perfect. So see how easy these marks are, okay? So these are the marks you should definitely be getting, okay? Because they're the simplest things. It's just memorizing. Proton is +1 and electrons are very small. Okay, and similar to what we did before, carbon can exist in 2 forms, diamond and graphite. Complete the diagram, show the electronic structure of carbon. It will always tell you the number of electrons, okay? So tell me, how many electrons am I drawing in this first shell? 2, perfect, 2 electrons. And how many am I drawing in this outer shell? So we've got 6 to begin with. We've taken off 2, so now left with 1, 2, 3. Brilliant, okay? You see, it's so simple, okay? Very, very simple mark. You just know everything wants to have the 2, 8, 8 structure, so you can have up to 8 in each, the second and third shell. So you've only got 4, so you put 4 in there. Okay. Now, atoms of fluorine with a different number of neutrons are called what? So we have 3 answers here: alkalis, alloys, and isotope. I really hope you all know what this is. Different number of neutrons. Thank you everyone for answering correctly. It's isotopes. Okay, no doubt about that. We all know as soon as it says different number of neutrons, we know it's an isotope, okay? So that's the key thing. And remember, isotopes do not change their charge. do not change their chemical property. They don't become positive or negative. They're just the same. They just weigh more or weigh less. Okay, so the mass number is the only thing that changes. Okay, if you want to remember one thing about isotopes, just remember mass number is all that changes, and you can calculate everything else from there. Well done. That was a lot, and it was quite fast. Please, I will be here. Just ask me any questions if you do have any. We'll come back at 11 a.m. So go and stand around, have a walk, have a cup of tea or water, and then we'll come back. Please do ask questions if you have any, okay? Hey everyone, welcome back. We're going to go into the next part now. We'll talk a bit about elements and the periodic table. I hope you're all back from your break and had a nice 15 minutes off. I know that went really quickly for me anyway. So what we're going to talk now is about elements. So we all know what atoms are. So they're the smallest part of an element. So what is this? And I hope you all know what this is here. This is the diagram of what? The periodic table, well done. So this is the periodic table, okay? And the periodic table, now this is not a full version of the periodic table, but the periodic table contains all the elements, all the elements that are discovered, and it lists them in a particular way. So it's listed in actually a very specific way. So even these gaps you see here is there for a specific reason. Does anyone know how they ordered these elements in the periodic table? So how do we know this comes first, this comes second? What is it ordered by? Who knows? How is it ordered? So someone has said atomic number, and that is absolutely correct. So they're all ordered by the atomic number, which is also the number of protons, which we know is mostly also the number of electrons, okay? So this has got 1, and then we go 2, 3, 4, 5, 6, 7, 8. You get the point, okay? So this is actually ordered in terms of the atomic number. And so that means that the lightest element is here, and the heaviest element is usually down the bottom here, okay? Okay. And we've also got the definition of an element, which is basically a substance that contains only one type of atom. So we know all of these in a lithium element have lithium atoms, okay? You don't have a mixture of any other atoms in there. And that's a very basic definition of an element, okay? So they're listed in order of atomic number, as we said. So the number of protons is how they're ordered, okay? And it's done in a very specific way. Now, why do we have these gaps here? Like, why is it randomly broken up here? Who knows? Exactly, and that reason is, someone said, is because of these different properties, okay? So if you look at the way the periodic table is, elements with the same properties are in columns known as a group. So these columns are also known as groups, okay? So we have, as you can see, also numbered 1, group 2, group 3, 4, 5, 6, 7, and then group 0 is called group 0 for a reason which we'll go into, okay? So these going downwards are groups. And these going across also have slightly similar properties as well. And these are called periods, or the columns, okay? So the thing to remember is that the elements in the same group have the same number of electrons in the outer shell, okay? And that's the most important thing to remember. So all of these in group 1 have the same number of electrons in the outer shell. All of these in group 5 have the same number of electrons in the outer shell. All of these in group 7 have the same number of electrons in the outer shell, okay? Now, can anyone tell me, just by looking at these, how many electrons do you think the group 1 elements have in the outer shell? And the clue is actually in the picture, it tells you. Perfect, so you have, all of these have 1 electron. And group 2 all have 2 electrons. And group 6 have 6, group 7 have 7, group 4 have 4, group 3 have 3, okay? So what about group 0? Why is it 0? Now it's 0 because they have full outer shell. Now we know that these all have the 2-8 configuration, which is what we need. These are known as the noble gases, okay? So the reason they're 0 because they do have electrons in their outer shells, but actually they don't have any spare electrons, which is what the number is for. So the number is the extra electrons they have, so the 1 and the 2. These have a full outer shell of 288, so they don't need to have another number, okay? So remember, the groups are the number of electrons in the outer shells, and actually every time you go down these columns, so these rows, what do you think you add on? So you obviously add on more electrons overall because you get more protons, so you have to add more electrons. But every time you go from this to this, you add an extra shell. So helium is, so hydrogen's got 1 shell, lithium has got 2. And as you go down to sodium, you got 3 shells, then 4 shells, then 5, 6, 7. Okay, so the column, the period, is the number of shells, and the group is the number of electrons in the outer shell. Okay, now this makes things very easy for you to remember. So whenever you get a periodic table in your exam, the first thing to do is just write 1, 2, 3, 4, 5, 6, 7, 0. Okay, and then straight away, you know, if they pick this element here, you know, phosphorus, okay, must have 5 electrons in an outer shell. You know straight away. Okay, you don't have to do any calculating. You don't have to look at the proton number and say, okay, it's 288. You just know straight away if it's in group 5, it's got 5 electrons. Okay, nice and simple. And the reason it's called a periodic table is because similar properties occur at regular intervals, which are known as periods. So things that occur regularly. Does that all make sense? So do you know, someone actually mentioned already, what is this line for? What do you think this line is here randomly for? What does this separate? Why do we have this random thick line here? Well done, someone said, splits metals and non-metals. Okay, so everything up here is non-metal. Everything down here is a metal. Okay, so you don't necessarily need to have this line. Okay, it doesn't really matter. You won't really get asked about these rare ones down here unless they specify it to you. But if you just remember everything on this line here, especially these ones and these ones are non-metals, you will just remember that the top right is non-metals and everything else is metals. Okay, and the reason that's important to remember is mainly for this thing here, is that metals tend to form positive ions and non-metals tend to form negative ions. I say 10 because there are some exceptions, but generally non-metals form negative ions and metals form positive ions. Okay, so what are some of the differences between metals and non-metals? This is going way back to like GCSE level, just simple things. What are some of the properties of a metal? Now you can tell me the most simplest thing you know about a metal and honestly it'll be right. Okay, tell me, what do you know about the properties of metals? And bring this back to as simple as you can do. So what can metals do? What can they not do? So gold, yes, gold is a metal. What else? Tell me about gold, for example. So it's shiny. Honestly, it's as simple as that is the right answer. Conducts electricity, well done. Anything else? What else can they conduct in addition to electricity, usually? If you're thinking about if you put a metal pan onto the stove, why does it cook the food? Because it conducts electricity through that metal pan and you get heat. So it conducts electricity and heat. What else? Are they soft, strong, hard, liquid, metal, I mean solid? So they're quite strong. They tend to be solids or liquids. I know there's a combination, but generally, so perfect. They're generally solids. And in terms of, so does anyone know what malleability means? What does it mean by something being malleable? It means it can be bent into shape, okay? So if you think about, for example, gold ring, you can bend the gold into shape. Or copper wires, you can make wires into copper. These are all malleable, okay? So these are all features of metals. Now this may seem very, very basic and easy to you, but these are questions that they ask you in your exam, which are very easy marks to get, okay? So just knowing 3 properties is really important. So they conduct electricity, they conduct heat, they're malleable, they're mostly solid, they're quite strong and dense. These are things you need. So the opposite of that would be most non-metals. Now, do you remember there are some metals which are liquid, for example, mercury, which is a liquid metal, which is what you get in thermometers. But actually that's, you know, the only one I can think of, and most of them are solids. But what about non-metals? Are non-metals shiny or are they dull? That was a bit of a leading question. They're dull. And are they strong or weak? Weak. Anything else you know about non-metals? Conductors, non-conductors? Maybe mixture of both, what do you think? They're poor conductors or non-conductors, okay? So if you put, like, example, like a wooden spoon in the stove, it's just going to burn. You're not going to get heat going through. You're just going to get the heat burning it, okay? So very, very simple table of the differences between metals and non-metals, okay? Because they may give you an element that you don't know where it is on the periodic table and say, this is a solid, shiny, malleable element, which is a good conductor of heat. Is it metal, non-metal? And you know straight away, actually, this must be a metal. So moving on to the noble gases, which is our first set of that we're going to go through, which, as I mentioned, is like the superheroes of the periodic table. Okay, they are perfect. They can't do anything wrong. They have everything perfectly arranged for them. The electron arrangement is perfect, and they are right there at the end with the group 0 at the end there. So tell me, what does anyone know about the noble gases? Okay, and the name should be in the clue. The clue should be in the name. Sorry. So what can you tell me? Someone can tell me anything about the noble gases. What is it? So one, we have the full outer shell. Stable, I like that word. Stable. Anything else? Gases, well done. Okay, so honestly, the exam sometimes, simple things are the right answer, okay? It tells me the noble gases, we know straight away, they must all be gases, okay? That is an answer. If they ask you, tell you about noble gases, they're gases, okay? Stable, exact cells, written unreactive. Perfect. Now, you know all these things, so you know they're gases. We know they're in the group 0 of the periodic table. We know they have a full outer shell, and we know they're unreactive. But can someone tell me, why are they unreactive? Why do they not want to react? Okay, and again, the answer is on the sheet, on the paper. Why do we know that they're unreactive, and how can we be sure of that? Why would this helium not want to react, or this neon? And exactly, the answer is here. They have a full outer shell. So the only reason an element would want to react is because it wants to get to the superpower of having a full outer shell, okay? So all of these other elements, so this hydrogen, this lithium, which has only got 1 electron outer shell, it wants to get rid of that and make it a full outer shell, so it only has 288. Whereas this does not need to react with anything to get that. So there's no need for this to form, to lose or gain electrons. It wants to keep its electrons and its protons as close to itself as possible, so it can't react, okay? Because if it reacts, it means it may lose or gain an electron, and that will mean that it doesn't have a full outer shell, okay? And that's not what it wants to be, okay? So they are unreactive because they have a stable arrangement of electrons. They all have 8. So apart from helium, which has just got 2 electrons in total, so it's only got 2 in its outer shell, they all have 8 electrons in the outer shell. So apart from, helium, which has only got 2 electrons. So they all have the 2-8-8 structure. Okay, so that's why they are not reactive. Okay, so if someone says to you why they're not reactive, the answer is because they have a full outer shell. Okay, and that's the answer you need to give. Very, very simple. So they exist as a single molecule, so you'll never see a helium as a helium-2 or helium-3 or helium-4. Okay, they don't even want to react with themselves. Okay, and that's how much of a superpower they are. They only want to be just helium, just neon, okay? You'll never see a number next to it because that means that there's 2 neon molecules reacting with each other, and that doesn't want to happen, okay? So even this does not happen, okay? So noble gases, they don't react, they are gases, and they have stable arrangement of electrons and a full outer shell. So I already know 3 or 4 facts about the noble gases. So we know they're gases, so that's one thing. Are they metals or non-metals? Remember what side of the periodic table they're on. So, and so that's why helium differs. So helium is different because it only has 2 electrons. So it does have a full outer shell, but that outer shell only has 2 electrons, whereas the rest of them all have 8 in the outer shell. So the rest of them all have 8, helium has 2, but that's the only reason. So they are all non-metals, well done. So remember what side they are of the periodic table, the top right side, which is the non-metals. So what do you think about boiling points and the melting points of noble gases? Low or high? And this is true for most of the non-metals. So if you think about gases, they're already essentially like condensed. So they tend to have low boiling points. But actually, one thing to remember is that the boiling points increase as you go down. So as they get heavier, they become harder to boil off and break down, but we'll go into that in a bit more detail later. So I know there's loads of colors here in this section, but actually one thing to remember about the noble gases is that they don't have any color. Okay, they're all completely colorless gases, so you can't see them. Okay, so if you think about helium in a balloon, you can't see it. So remember, if you can't see helium, you can't see any of the noble gases. Okay, so you can't see any of these, whereas other gases, which you'll see, actually do have colors to them. And as we know, they're unreactive, because they have stable electron arrangements. Okay, so 288. So just to make sure you were listening before, we're going to do a quick quiz, quick question. What do you think? Elements in the periodic table are listed in order of the atomic number. Excellent, well done. So you're all answering. And the majority of you are absolutely correct in that it's true. So they all get ordered in the atomic number, which is also the proton number. Okay, so they get heavier. And one more question about the noble gases, just to make sure you were definitely listening. The noble gases are unreactive. Why are they unreactive? Why do you think they're unreactive? Excellent, you're all answering. Well done, everyone. So, as you can see, most of you, almost all of you got that right, that they have a full outer shell of electrons, okay? So this is not a correct answer because non-metals can be very reactive, and you'll see later that you can have very reactive non-metals. Gases can also be reactive. It's not a reason in itself for it to be non-reactive, and they don't even react with each other. Remember, they don't come as He2, they always come as itself, okay? So very good, well done. So then we have this group here, group 1, and this is known as the alkali metals. So I don't even need to ask, metals or non-metals, you should all know they are metals. It's in the name, but also they're the furthest you can get on the left, so they must be non-metals, okay? Sorry, they must be metals, ignore. They must be metals, okay? Because we said top right is the non-metals and everything on the left is metals, so this definitely must be metals, okay? So how many electrons did the alkali metals have in their outer shell, okay? Remember how you remembered to learn this. How many electrons do they have in the outer shell? Who knows? 1, well done, 1. So if you remember that lithium atom we saw before, and it had a 7 and it had a 3, okay? So we can calculate already how many, even if you don't know, if you get the atomic number. So you must have the lithium in the middle with the protons and neutrons, and in the first shell, you must have 2, and that leaves just 1 electron in the outer shell. Do you see? So even if you don't know the group number, you can calculate it out if you have this. Okay, so we know it's got 3. So the next thing, then you have sodium, okay? So sodium also has 1 electron in its outer shell. So if anyone asks us to draw the sodium configuration, we can do it very, very easily. So we don't even need to know the total atomic number. We know it must have 2 in its first shell. If it's got 3 shells, the second shell must have 8. And then we know it's in group 1, so it's got 1 electron in its outer shell. So again, we know this has got 1 shell, 2 shells, 3 shells. Yeah? So we know it must have 3 shells. So who can tell me how many electrons does sodium have? So 2, 8, 1. It must have 11. So straight away, I know that the atomic number equals 11, okay? But anyway, the most important thing is the number of electrons is 11. And it's got 3 shells. And then similarly, I'm not going to go through it, potassium will have 3 shells, so this is in, sorry, 4 shells even, and it will have 2, 8, 8, and then 1 electron in its outer shell. Okay? So very, very easy way to remember. All the group 1 elements have 1 electron in the outer shell, and as you go down, you add 1 extra shell. Okay? But regardless of how many electrons they have in total, the outer shell always has 1 electron. Okay, and the thing about alkali metals, they are metals, but they are soft metals. So if you were ever to do any experiments in school, you may be able to work with these. You can see they're all very soft. They can be cut with a knife. So you know those things you see sometimes when you can cut them, it's like a solid piece that you can cut with a knife. That will normally be something like an alkali metal. But they're all solid. So they are solid soft metals and they are very reactive. Now, if you think, they all want to get to the structure of the noble gases, which is by having a full outer electron shell, which either having 2 or 8 in the outer shell, okay? Now, if you think about lithium, which has got just 1 electron in its outer shell, so 1 here and then 1 here, the easiest way for lithium to get a full outer shell is either to gain 7 electrons to make it 8, or just to lose this electron and make it 2. So what does it do? The easiest way is to get rid of this electron. So if you can imagine, it's buzzing to get rid of that electron. It really, really wants to get rid of that electron, because as soon as it gets rid of that electron, it becomes like a noble gas where it has 288, okay? Or in this case, just 2, okay? So that makes these all very, very reactive, because it's very easy for them. They think it's so easy for me to get the superpower structure. All I need to do is get rid of one electron. So they're looking for anything that they can do to get rid of that 1 electron. Okay, so they're very reactive. So they're so reactive, in fact, that if you were to hold it in your hand, it will react with the oxygen around it. If you were to put it in water, it reacts with the water it's in, okay? So you can't even let it react with the air, because it's so reactive that even if you put it next to oxygen, it'll want to react, okay? And that's important. So as you can see going down, you know 2 things, okay? So you know that every single one of these has 1 electron in its outer shell. And the second thing you know is that there are more shells as you're going down, okay? And so you know if it's got more shells, it means they're all having more electrons. Okay, more electrons, they have more protons, and they are heavier. Okay, so that automatically means they must be getting bigger. Okay, you know it's getting bigger because as you go further down the periodic table, the mass number is increasing because you have more protons. Okay, and we know the periodic table is ordered by atomic number, which is the number of protons. So as you go further down, you're getting heavier and heavier because you're getting more protons. So 2 things happen. So as you're going down, I'm just get rid of this here to show you. As you're going down, one thing you have is that in lithium, you have the positive nucleus here, and you have just 2 shells, and this electron here, which is what it wants to get rid of. And then as you go further down to the bottom one, for example, or the lower ones, you have loads and loads of shells. Okay. And again, 1 electron in the outer shell. Now, which one do you think will be more reactive and why? Does anyone know which one of these is more reactive? The higher one, which is lithium, or the lower one, which we'll just say is francium? Which one is much more reactive? So we're getting a combination. Okay, we're actually getting exactly a half combination. So actually the answer is this one, okay? And the reason is for 2 things. So remember, the way that these alkali metals want to react is want to get rid of this electron. So they want to get rid of this electron completely. Now, if you think about this one, here you have a positive charge here, and here you have the negative charge of the electron. Now, you can see it's very, very close to each other. So this positive charge is holding on to that electron. It's kind of really grabbing onto it. And the positive charge doesn't want to get rid of the electron, you know, just like a magnet, opposites attract. The positive charge and negative charge are very, very attracted to each other. So in this case, the distance is much longer. It's a much bigger distance. So that attraction from that positive charge in the middle is actually a bit weaker. So it's a little bit easier for this electron to come off and go somewhere else than it is for this one. And that's because the distance between the positive nucleus and the electron is increased because of the number of shells. Now, the second thing to remember is if you have this positive nucleus, which is the only thing holding that electron together, it's the one thing that's holding that electron in place because of this negative and positive attraction. Now, if you think you have 1, 2, 3, 4, maybe even more of these shells can kind of block that positive charge pulling that electron, and that's got a name to it. What do you think it's called? What do you think these orbits are doing, these shells are doing, that stops that strong attraction between the positive and negative charge? It's actually forming like a shield. So this is forming what we call a shielding effect. So if you imagine all of these little orbits are forming a shield to stop that positive charge holding on to that negative electron, okay? So there's 2 things that happen. So firstly, you're getting further away from the positive charge as you go down. You're getting much further away from the positive nucleus because you're getting bigger atoms. And secondly, with every single orbit that you add, you're adding an extra shield. So you have a shielding effect. So that means as you go down, they become much more reactive because it's much easier for them to lose this negative electron that they're trying to hold on to. Does that make sense? So now we all know that they get larger, so as they get bigger, there's less positive attraction and there's shielding effect. So that means it's much, much more reactive. So key points from this page is as you go down, the alkali metals become more reactive. And it's usually a 2-point mark. Why does it become more reactive? Because it's further away from the positive, the electron that you're trying to lose is further away from the positive nucleus. And 2, there's a shielding effect from the increased number of shells. Okay, so those are your 2, sometimes 3 marks for that question. So the alkali metals react, so they react with a number of things. And the most common thing that they react with is always, it's a metal, it always reacts with a non-metal, okay? So remember, non-metals are the ones right at the end of the periodic table, okay? Usually you get metals reacting with non-metals in this case, okay? So they react with oxygen. Does anyone know how, so let's, for example, use sodium. So when sodium reacts with oxygen, what do you get? So oxygen always comes as O2. What do you get? Very straightforward, sodium oxide, okay? And you don't need to know these at the moment. We go into these in a bit more detail in a further lesson, but just to give you an idea for this. And they react with chlorine. So anyone know what you get when you react with sodium plus chlorine? So chlorine, remember, is a gas. What do you get when you react sodium with chlorine? Sodium chloride, perfect. So it's NaCl, okay? And then, so sodium chloride, okay? So when chlorine becomes mixed with sodium, it becomes chloride. Again, we're going into this further in a different lesson, okay? But just so that you're aware. And the reaction with water, you get sodium hydroxide plus hydrogen, okay? Again, these will go into a lot more detail in a further lesson, but just so that you're aware, they react with loads of different things, okay? Usually non-metals. So we said that you get increased reactivity. Who can tell? So I told you the 2 main reasons. Who can tell me what one reason as to why you get increased reactivity as you go down with the alkali metals? So they want to lose 1 electron. So 2 answers. So 1 is yes, so it's further away from the positive nucleus. And what was the other word we used? That tells you what is the word that you need to use in your exam to get you the 2nd point. Remember, we have increased number of shells. What's that effect called? Shielding, okay? So this is a very, very common exam question, okay? So you need to know they get more reactive is the first point, so as you go down. And the reason is because they need to lose an electron, and it's easier to do that when they're further away from the nucleus, because they're further away from that positive charge that's holding them in place. And secondly, and so it's less attracted to this nucleus, easier to lose, okay? So if you remember that they have 1 electron in the outer shell, the easiest way for them to get a full outer shell structure is to lose that electron, and then you will know that by doing that, they need to be further away from the positive center where the protons are, and the more shells there are, the more likely they will be having the shielding effect, and that means that it'll be easier for us to pluck that electron off and add it to something different. Okay, so important things to know is shielding effect, and the bigger they are, the further away they are from the positive nucleus. So, who remembers what some of the features are of alkali metals, okay? Now remember, we did go through metals, but specifically alkali metals are a little bit different to normal metals. Which of the following are features of alkali metals? Now if you remember these, there's 3 in every single question. If you remember just 3, you know the features of all alkali metals. Few more left to answer, and then Perfect. So well done. So everyone knows they are soft, solid, and reactive. I mean, with this question, straight away, we can cross off B and C because we know this is completely incorrect. They all have one electron in the outer shell, and they want to do whatever they can to get rid of that so that they can have a full structure like the noble gases. So they will react with anything, okay? So, and please tell me everyone knows this because I've been banging on about it from the beginning. How many electrons do alkali metals have in the outer shell? It's not a trick question. It's honestly as simple as it is. What do you think? How many electrons in the outer shell? I think some of you are just trying to be funny because it definitely is one electron, okay? Alkali metals are group 1 and they all have one electron in their outer shell. Okay, well done guys. So alkali metals are group 1, okay? And like I said, even if you don't know or don't remember their group 1 or don't remember something as an alkali metal, you can calculate how many electrons in the outer shell by using the mass and atomic number, okay, as we showed you before. Okay, slightly more wordier question, but see what you think. Which of the following is not a reason as to why alkali metals are more reactive as you go down the group? The shielding effect, the outer electron is further away from the nucleus, or there are more protons as you go down? Which is not a reason? So which of these is not a reason? Okay, so this question is I think maybe it's a matter of reading the question. So we're going to go through this one because we've got half of you thinking A and half of you thinking C. I think someone's misclicked and clicked D, but what we're going to go through. So why are alkali? So the question is asking why are alkali metals more reactive as you go down? That's the first thing you need to do. So if you get a question asking something like this, okay, so don't even look at the answers. Just think to yourself, why are they more reactive as you go down? You have one answer is, as we all said, shielding. So this is a reason. And 2 is because it's the bigger the atom, the further away the electron is from the nucleus, okay? So having more protons is actually something that works against that. Because if you have more protons, you have more positive charge, which is attracting that negative electron more. So actually, this is something that works against it becoming more reactive. In fact, the reason that this doesn't make much of a difference is because these two things together add more in allowing that electron to be removed, okay? So the reason it's not more reactive is the answer is C, okay? This is the reason that would make it less reactive, because that means there are more positive charges holding that electron, okay? Which is true. So as you go down, as you know, the atomic number increases as you're going across the periodic table. So the number of protons must increase. So you might think, so well, why isn't that causing the electron to be more firmly held? Because actually these two things outweigh it, okay? So yes, there are more protons, so there is more positive charge trying to hold that electron, but actually as you go down, the reason it still becomes more reactive is because the shielding effect and the bigger atom outweigh this. Does that make sense? And I'm going to relaunch this, and I want everyone to think about the question and answer correctly and understand. Do not answer if you don't understand. If you understand this, please answer correctly. And if you don't understand, just so I can see that you all understand that the protons is not, the reason it's more reactive is because of A and B. Okay? Good, well done. Okay, so you all get it now, okay? Okay, so we've gone through the noble gases, which all have the 288 structure. We've gone through the alkali metals, which are in group 1. And now we're going through back this side to the halogens. And there's a reason why we're doing it in this order, okay? Don't worry, this isn't just completely random, okay? Who knows anything about the halogens, okay? And even if you know nothing, from what I've taught you, you should know one thing about the halogens, okay? Just by looking at what we've taught you so far. What do you know about the halogens, which are these elements here in this group here? So straight away, you should know okay, so 2 things. So one thing, they are non-metals. Oh, sorry, my pen got done. So, okay, definitely, you guys all definitely say one is they're non-metals. Oh. If you know when cheated there, so non-metals. And 2, perfect, they're in group 7, so they must have 7 electrons in the outer shell. This is important, okay? So you see, you don't even need to know anything else about them. You know straight away, 1, they're non-metals, and 2, they have 7 electrons in the outer shell, okay? So tell me, someone's actually already said to me, so what does that mean? So if they have, so for example, let's take fluorine, okay? It's got 1, 2, 3, 4, 5, 6, 7, okay, and 2 here, okay? So this wants to get a noble gas structure, which is having 2, 8, 8, okay? So it wants to have 8 or 2 electrons in the outer shell. What's the easiest way for it to do this? So we know with the alkyl metals, they need to just lose 1 electron to get this. For the halogens, how many electrons will they have to lose? They have to lose 7, okay? And that's very difficult. But how will they get 8 electrons? Exactly. So you've all said they just need to gain an electron from something else to make a full structure. So they only need 1 electron, okay? So instead of losing 7 electrons, which is going to take ages, it's easier for them to gain an electron to make a full outer shell structure, okay? So how do they do this? So they react with something that wants to get rid of that electron, okay? So we already know what the answer there is. These want to get rid of it, these want to gain it. So you can imagine these two become very good friends and like to react with each other, okay? So group 7 have 7 electrons in outer shell, okay? So we know that. They only need 1 electron, so they are very reactive. So if you need to just gain or lose an electron, it makes you very reactive because it's very easy to do that. And you know, I only have to do this one thing and I can become a noble gas. So they're very reactive, okay? And they come in 2s, okay? So the halogens always come in 2s. So you always get fluorine as F2, fluorine as Cl2, bromine as Br2, okay? So remember, the halogen always comes in 2s. So whenever you're writing in an equation, you always have to put a 2. So remember, helium and neon and the noble gases are always on their own. They don't want to react even with themselves. Whereas these guys, they do want to buddy up and make 2 together, okay? So what are some of the properties of the halogens? So we already said they are non-metals, okay? That's already 1 mark, okay? Easiest mark you'll get is by saying something a metal or non-metal when they ask you about property. So do you think that they react with metals or non-metals based on what I told you before about this group here and they are having 1 electron? So what do you think they react with? Yes, so they react with metals. What else do you know about them? Do you know what structure they are? That's a bit of a trick question. But do you know what structure the gases are? Sorry, the halogens are, and that wasn't the answer. They are actually a mixture of both. So fluorine and chlorine are gases. Bromine and iodine are liquids. And iodine can also be a solid. Okay, so they go from gas to more solid. Okay, so they're a mixture of both. So actually, they're all non-metals, as we said. They have low melting and boiling points. I think most things that are gases and liquids will have low boiling points, okay? Whereas if you have something solid, thinking about boiling a solid thing is going to take much longer. But the melting and boiling point increases going down the group, so it's harder to break them up as they get bigger, okay? And if you think about what I said, they start as gases and they go down to solids. We already know they react with non-metals because by sharing electrons to form compounds, and we'll go into that when we go into bonding. And the way that they do that is because the metals transfer 1 electron to the halogens to form a complete outer shell of ions. And so that's why they always gain an electron, because we know they want to gain an electron to make a full outer shell because they only have 7. So they will always become negative ions. So if you remember, if you have, for example, chlorine and you add an electron to it, it will become Cl minus because now you have 1 more electron than proton. Does that bit make sense and why they become negative, okay? Because in order for them to have a full outer shell, they only have 7 electrons in the outer shell. They want to have 8. So if they're getting an extra electron, they're getting an extra negative charge. Whereas before they were neutral, but now they're gaining a negative charge because they're gaining an electron. So they will always form 1 minus ions, okay? And we're going to go into what ions are as well. So reactivity, who can tell me how the reactivity changes? So we know that alkaline metals become more reactive as you go down. What do you think about the group 7 elements? More reactive as you go down or less reactive when you come down? Who can tell me more or less reactive as you go down the group? Perfect. Everyone's saying less reactive, okay? So they become less reactive as you go down. Now, if you can imagine, it's a similar situation to before. So if you have, for example, chlorine, which is very, very small, and you've got these 7 electrons, and is trying to attract this electron. Now, the positive charge here is very, very close to that electron, so it wants to grab it. So it's really easy. Whereas if you have something like iodine, which has got loads of shells and loads of electrons, and you want to attract this electron, that proton with the positive charge is very, very fast. So it's much harder for it to get there, to be attracted to attach here. So it's exactly the opposite of the alkaline metals. It's less reactive because you're further away from that positive nucleus. So it's much less likely to attract this negative charge. If this electron was here between these two, it would definitely jump to this one first because this positive charge is much closer and easier to grab onto than it is this one. Does that make sense? So less reactive as you go down. So they react with a number of different things. So they can react with hydrogen to make hydrogen fluoride. This again we'll go into another way, just so you can have a look. So F2, F2, and 2 hydrogen fluoride. They also react with metals. So as we said, sodium from group 1 and chloride makes sodium chloride. Okay, so remember the chlorine becomes a negative charge and the sodium becomes a positive charge. And we're going to go into this when you talk about ionic bonding later. Okay, so you form compounds with metals and non-metals to make a compound here. But the key thing is they become less reactive as they go down. So we said, why do they become less reactive? Because the electron that needs to be attached needs to be closer to the nucleus, and as they go down, they get bigger, they have more shells, and so it's less attracted to the positive charge. Because similarly because the shielding works in the opposite sense here. In the beginning, the shielding makes it more reactive in alkaline metals because it allows lots of kind of shield to be in place so the electron is easily removed. Whereas here, if you're trying to attract that electron, you have all these orbits in the middle. It's difficult for you to get that electron onto that shell. So you can actually tell that reactivity by looking at halogens reacting with each other. So what you can do is if you have, for example, this sodium chloride, and you mix it with, for example, some bromine, which is, sorry, let's do the opposite. So if you have sodium chloride and you add in fluorine, which is above it, then what will happen is that fluorine, because it's more reactive, it will replace the sodium chloride and make sodium fluoride. Okay, whereas if you were to add bromine to this, which is bromine is below chlorine, nothing will happen. Okay, whereas if you have, for example, something with iodine and you add bromine, the bromine will replace the iodine because it's much more reactive, because as we go down, the reactivity decreases. Okay, so if you remember, if you have something like, I'll just show you what this page here so you can see. So if you have sodium chloride, which one of these do I have to add to make it replace the chlorine? Which one of these can I add that will replace the chlorine? There's only one. Yeah, so the answer is fluorine. So if I add F2, then this will then change. The fluorine will become more reactive, will take rid of this and make this sodium fluoride. Okay, so that's how it works. Okay, whereas if I were to add some bromine to sodium chloride, nothing will happen because it's not as reactive. So that's what you can call displacement. Okay, so it can displace. So a stronger, so a more reactive element can replace a less reactive element in displacement reaction. Does that all make sense? I hope it does. So in summary, we know that the halogens need to gain 1 electron in order to get a noble gas structure. And the further down the group, the electron gain is further away from the nucleus, so less strongly attracted to that positive charge and so harder to gain. Okay, and this is just showing you again an example of chlorine replacing bromine by taking over the potassium chloride. Because if you remember, bromine is below chlorine. Okay, so it's less reactive. So in this case, the chlorine, which is more reactive than the bromine, will overtake it and form potassium chloride. Okay, whereas if you add something that was less reactive, nothing would happen. So this is a bit of a hard question, and I just want to see if you remember how chlorine comes in a normal form and how sodium comes in a normal form. Have a proper think and see what you think. So remember how I said that the halogens always come in a specific way. They always like to buddy up, should I say. So remember one thing I said, that the chlorines and the halogens always like to buddy up. So you don't have to know anything else in this question. Apart from that, chlorines like to buddy up, and that should give you the answer for the equation. You don't even need to know the equation. Okay, so I think most of you know that you get sodium chloride, which is NaCl. The key thing to remember is that this is the answer because chlorine always comes as Cl2. So even without knowing what the equation is, you can know straight away, this can't be right, this can't be right, and that can't be right, okay? So this is an exam technique that I'm trying to teach you so that you won't always know the answer when you're looking at a question, okay? You won't always know, and it won't always be as simple, but you can cross off 3 things. The thing you need to do is eliminate the incorrect answers, okay? So now you'll remember always, thankfully, that the halogens, so fluorine, chlorine, bromine, iodine, will always come as what we call a diatomic molecule. So they'll have a 2. So always be as iodine 2, bromine 2, okay? So I didn't expect you guys to know the formula for this question. What I expected you to remember is actually that chlorine always comes as Cl2. You will never get chlorine on its own, okay? And so by knowing just that, you don't need to memorize or remember the equation between sodium and chloride. You just need to know it can't be these because chlorine has to come in 2. So even if you're not sure, is this the answer, is it not? You know it can't be these, and so this must be the answer, okay? So this is what is a very, very important exam technique. You always should eliminate what you know. If you don't know the answer to a question, eliminate the incorrect answers, okay? And remember, halogens always come as pair, okay? So it will always be a Cl2. So straight away, you know these can't be right, okay? It was a bit of a trick question, but actually, hopefully you've learned that technique. Okay. So we've got the diagram of the halogen next for you to see. Which one of these is the most reactive? And before you answer, have a think. What makes them reactive? Remember, they need to gain an electron, and what will make them gain that electron? Okay, the smaller ones at the top or the big ones at the bottom? Okay, this is more reassuring. Well done. So I can see that the majority of you, give you a few more seconds for more people to answer, just to make sure. Perfect. So well done, everyone. So we know fluorine is the most reactive because it's the smallest, and so that electron that needs to come in is close to the positive nucleus. Okay. So this is another question, which is a little bit, I wouldn't say a trick question, but it's checking what you remember from before. Which of these halogens have the lowest atomic number? Okay. Now remember what atomic number means, and remember how you can apply that without knowing specifically what the atomic numbers are. Which has the lowest atomic number? Okay, I'll give you a few minutes for more people to answer. Okay, well, the good thing is I'm seeing that most of you put either the top or the bottom one. So remember, atomic number is the number of protons, okay? And we know that the periodic table is ordered in order of atomic number, which means that the smaller ones, if you remember what the periodic table looks like, the smaller ones are over here and the biggest ones are down here. So as you go across, you get increasing atomic number. So that means that as you go down, you have increasing atomic number. So that means the one with the highest atomic number must be, in this case, iodine. Okay, sorry, the lowest atomic number, sorry, the lowest is fluorine, you're right, sorry. The lowest atomic number is fluorine and the highest is iodine, or this one here, okay? So whenever you're looking at a group, it always increases in atomic number as you're going down, whichever group that is, group 1, 2, 3, 5, 6, 7, always atomic number is increasing as you're going down. And remember, the periodic table is ordered in order of atomic number, so it's only one direction it can go. It can only go higher as you're going down, okay? I hope that was okay. And final question, which I hope you all know, I'm not even going to remind you what group it's in, and hopefully you remember. How many electrons does the halogens have in the outer shell? Well done, everyone. So that's excellent. So 7. So we know they have 7, so they're in group 7. And in order to get the 8 structure, they need to gain 1 electron. Okay? So I'm hoping that covers the halogens for you and you remember that, because now we're going to move on to the transition metals. So the transition metals, as you can see, they don't have a group number. Does anyone know why that is? Why do they not have a group number? Why do you think they don't have, why do you think there's a big gap here and these ones don't have any group number? Does anyone know? Very impressed if you do, because it's actually more A-level going into transition metals. So firstly, we know one thing about them, they are metals. So you always have one thing that you can write about them. So the reason they don't have the same group numbers is because they can have variable charges. Okay, we know these will always become -1 charges. These will always become +1 charges. Sorry, opposite way. These always become +1 charges. These will always become -1. Whereas the transition metals, they can sometimes, you can get, for example, copper with 2+, or you can get with 3+. So they can gain or lose more electrons. So it's not in our interest for them to have numbers, because actually that number is not, with helium and lithium, it's always the same. They're always going to gain 1 electron, sorry, lose 1 electron. Whereas with these ones, it's never 100%. So you don't want to confuse people by putting a number with them, because that number can change. So iron, Fe iron, for example, can be 2+ or 3+ or 1+. So what's the use in putting it? So they have variable charges. Okay. And they're a bit weird that they have differing properties. So it's not like these where they all have similar properties and you can label them. They have mostly similar properties, but it's like I said, for example, mercury is a liquid and zinc is a metal, solid. It's very variable, and some of them you won't even have heard of. So that's why we can't put numbers next to them. So does anyone know anything about the transition metals? Now, if you think about what's in the transition metals, like iron, copper, nickel, sorry, that's cobalt, nickel, copper, zinc, these things make our everyday things, okay? And so that should help you. So I'm going to talk through a few things about the transition metals you should just need to know, okay, when it comes to the properties of them. So as you know, they are metals, so they are good conductors. So most conductors are metals, okay? So automatically, if something's a metal, you can just say good conductor, okay? Ductile means it can be stretched into wires. Now just think, what are wires made up of? Copper and steel and these things. So think copper wires, okay, so it must be able to stretch them into wires. Sonorous, which basically means they make a ringing sound when hit. If you think about anything metal, when you hit it like a dong bell and things like that, it should help. They're quite strong, so again, think about things like iron and copper and the things that you find are making buildings and like scaffolding. It should help you, okay? Malleable is an important word, which means it can be hammered into shape. And when we go through metallic bonding later, we'll talk about why that is and how that is. And again, they are shiny. So when we went through metals and non-metals, metals are shiny. And as usual, if you think about all the metals that you have, they have high melting and boiling points. Obviously, there are exceptions, okay? But generally, these are the properties of transition metals, okay? So I'm not going to go into too much detail about that because it's on there. You can have a look, but it's basically just a few things that you would put down in an exam question, okay? When it comes to reactivity of transition metals, because they are so different and they have variable trends, we can't actually say specifically what the reactivity, they won't ask in your exams anyway specifically what the trends are. But generally, what we would see is that the reactivity decreases across the period, okay? But there are a few exceptions, okay? Which is why there's no hard and fast rule for it, okay? But generally, reactivity decreases across the period, but there are exceptions such as zinc being very reactive, okay? So that's the main thing to be aware of, is that generally as they get bigger, they become less reactive, okay? And remember, they get bigger because you get increasing atomic number, because as you go along the periodic table, you have increase in proton number, and that's because they're ordered in their atomic number, okay? I hope that's one thing you all remember from this. So the next thing we're going to talk about is mixtures and compounds. Now, who can tell me what's the difference between a mixture and a compound? Tell me a few kind of buzzwords that you need to know for this. What's the difference between a mixture and a compound? And why do we need to establish that difference? So someone said, so mixtures can be separated. Perfect. Separated easily, I would say, because you can separate compounds, but not as easily. Perfect. So compounds is chemically bonded. Keyword there. Very, very good. Okay. So compounds, and yeah, so exactly, mixtures are not chemically joined together. So these are very important things. Okay. So mixtures are two or more substances that are mixed together, but are not chemically combined. So each substance in that mixture still has its own properties. They still act as they would do if they were not mixed. Okay. And that means that they can be easily separated because you do not need to involve any chemical reactions or any energy changes to separate them. Okay. It's very basic. A mixture is two things mixed together that can be easily separated that are not chemically bonded. And then a compound, as you said, is when there's a chemical reaction between elements, okay? And they are chemically bonded together and a chemical reaction takes place. So a lot of the word chemicals thrown around there, but you can see from this example here, in this mixture, you have oxygen molecules, oxygen, and then you have the hydrogen molecules. And in this compound here, you realize you have these two attached, these two attached, and these two attached. So the properties of the oxygen and the hydrogen here is very different here because hydrogen is the gas, oxygen is the gas, but what's H2O? It's a liquid. Could you see the difference? The properties of these of the elements in the mixture stay the same, but in the compound they can change. So whenever you have a chemical reaction that forms a change in the two substances, you get a detectable change in energy, and that's what you will be able to identify. For example, when two gases become a liquid, or when heat is given off, or something like that. So you get fizzing and bubbling, or for example, as you can see here, you can see this is it's getting much bigger. And when elements react with each other, as we have discussed before, you have electrons which are either being shared or transferred. Okay, and that's where we're going to go on when we talk about bonding. Now, this bit is more to do with the practical stuff that you're going to go. So I've put this slide in here for you to be able to reflect on and look at. But actually, this is the stuff you're going to do in your practical session. So we're not going to spend too much time on it in this section here. But the main thing is when it comes to mixtures, because they're not chemically bonded, as we said, you can easily separate them, okay? So even if you have, for example, two solid substance going into liquid substance and dissolving, you can still separate them out quite easily, okay? And these are the different mechanisms in which you can separate mixtures, okay? So filtration, crystallization, distillation, and chromatography. We're not going to talk about these in detail because this is definitely things that you need to see in practice in your experimental parts for you to be able to understand it. But I put this here just so that you're aware, and then when you do it in class, you can kind of reflect back and think, oh, actually, this is how you separate a mixture. So now it's almost 12 o'clock. So we're going to just take another half an hour break. So we'll see you back at 12:30. Well done. I know we've gone through quite a lot. I am still here if you want to ask any questions. And then the last part, we're talking about chemical bonds. Okay, so well done, guys. I'll see you back in about half an hour. Hello everyone, welcome back. I hope you all a bit rested after that half-an-hour break. Maybe have something to eat. We're just going to go on to the last section now, so you will have another break just before we finish. But just to go through, kind of tying everything we've done together now. So we've gone through atoms, we've gone through elements, we've gone through different, some of the different parts of the periodic table and how the different groups react. And then we're going to talk specifically about those bonds that they form. So we spoke previously about how the alkali metals want to lose an electron and how the halogens want to gain an electron. We're going to talk now about how those things happening cause chemical bonds to be formed. So this is an example of one of the types of bonding that we're going to go through. So you have a sodium here, which has got 1 electron in its outer shell, and a chlorine here, which has got 7 electrons in its outer shell. And what you can see here happening is you get a positive charge of the sodium ion when it loses an electron, and a negative charge for the chlorine. So what does anyone know what type of bonding this is? What do we call this kind of bonding? When you have a metal and a non-metal forming what we call ions. Well done. So glad to see you guys are back. So everyone's answering ionic bonding, okay? So we're going to talk into more detail about what this is in a bit, but it's good you know what it is. And then we have this here, which is loads of positive metal ion, well, it kind of gives it away, metal ions, and then you have these tiny little red electrons, okay? And you can see these are form very nice little layers they form. So they're all kind of really, really stacked nicely in a nice order, and you've got the positive metals with the electrons kind of floating around. What kind of bonding is this? Perfect, this is metallic bonding, okay? Again, it's in the name, so you have positive metal ions. And I'm not even going to show who knows what the last type of bonding we're going to go through is, since you guys are so good and know all types of bonds. Covalent bonding, well done. So with covalent bonding, if you can see what's happening, so the X is from the hydrogen, is the electron on the hydrogen ion, hydrogen atom, and the circles are the electrons in the chlorine atom. And what you can see here is that the hydrogen atom now has 2 electrons in its shell, and the chlorine atom has 8 electrons. So they both have the noble gas structure. But the only way they can do that is if they share these electrons, okay? So unlike the ionic bond where it's giving away this electron to the chlorine atom here they are sharing the electrons, okay? And that's called a covalent bond, okay? So that's just a very brief overview. We're going to go into more detail about each type of bond now to give you a better idea of how they occur, how they are attracted to each other, and what keeps them in place. So we'll start with ionic bonding. And in order to understand ionic bonding, we need to understand what ions are. So who can tell me what an ion is? Okay, we've briefly gone over it, but what's the definition of an ion? Perfect, so it's what we call, you can also call it a charged atom, okay? So we know an atom is the smallest part of an element that exists. So for example, let's just pick if we have the lithium ion, okay? So if lithium, which we know is a group 1 alkali metal, loses this electron, so it's got this electron in the outer shell, if it loses this electron, then it's losing a negative charge, so it becomes +1. So does it make sense that when it's losing an electron, you're losing a negative charge? So if you have less negative, you're more positive. Does that make sense? It's a bit confusing. I hope it makes sense. So when you lose an electron, you become positive because now you have more protons than you have electrons. Okay, so lithium has 3 protons and 3 electrons. But when you lose an electron, you end up having 3 protons and 2 electrons. So now you have more positive than negative. Okay, so this is an ion. Similarly, when we talk about chlorine, so we know that chlorine has 7 electrons in its outer shell because it's in group 7. And in order for it to become a full outer shell, we know it needs to gain an electron. So if it gains an electron, that means now it's got more negative charge than positive charge. So chlorine becomes Cl-1. Okay, now lithium and chlorine here are atoms. So these 2 are atoms, but these 2 are ions. Okay, so the thing to remember is ions can be negative or positive. So as soon as you see an element or an atom, sorry, with a charge, it's become an ion. Okay, it's no longer just an atom, it's now a charged atom or an ion. Okay, so you can have positive ions, you can have negative ions. Okay, it becomes positive if it loses electrons, and it becomes negative if it gains electrons. Now, one way for you to remember this is, this is just at your level of chemistry, you will never ever gain or lose protons, okay? It will only be electrons, okay? So you will never lose or gain protons. You can only lose or gain electrons because electrons are floating about and they're easy to be plucked off. Whereas if you think where the protons are, they're in the middle with the nucleus, with the neutrons. So whenever you're gaining or losing positive, whenever you become positive or negative, it's always to do with electrons, okay? You're either losing or gaining electrons. It's never to do with losing or gaining protons. So just remember that. Becoming an ion is to do with losing or gaining electrons only, okay? So you're never becoming positive by gaining protons. That just doesn't happen, okay? You're becoming positive by losing a negative charge, by losing that electron. Okay, I hope that makes sense, okay? And yeah, someone has said that metals will always be positive ions, okay? And we'll see that as well in our examples. So atoms, as we know, do not carry charges, but ions, so remember that we said that all of the atoms that we see are neutral, and even the isotopes of those atoms are neutral. They don't have a charge. They only have a charge when they gain or lose electrons and become an ion, okay? So in an ion, they don't have the same number of protons and electrons. They must have more or less electrons. And remember, it's only the electrons, not the protons, that change. So you have this neutral atom with neutrons, protons, and then 3 electrons. Once you lose this electron, now this becomes positive because you have less negative charge compared to a positive charge. Okay, I hope that makes sense. I'm drilling it in just because it's important to not confuse getting a positive charge with gaining protons. It never happens. You only get a positive charge by losing electrons. Okay, only electrons move in and out of these atoms. And again, positive ions, they have more protons than electrons. Okay, so as soon as you lose an electron, that's it. You cause the shift and you're a negative ion. And negative ions have more electrons than protons because you've gained an electron. So I'm just going to talk briefly about hydrogen because hydrogen is a very, very strange type and it's very unique. So if you think hydrogen has got atomic number of 1, a mass number of 1, and that means it's literally just made up of 1 proton and 1 electron. There's no neutrons, okay, which is why the mass and proton number is the same, okay? So it's got 1 proton, 1 electron. This is what it looks like. So if you imagine, if it loses this 1 electron, all you're left with is 1 proton, or H plus, okay? So it's the only element where if it loses an electron, it won't have any electrons at all, okay? Every other element will have at least 1 or 2 electrons in its bare shell, whereas because hydrogen's only got 1 electron to begin with, as soon as it loses that electron, it's left with just 1 positive charge, okay? So this gives it a few special properties, which we're not going to go into today, but just so that you're aware, because that might confuse you if you see in your exam that, you know, you have this. So that means it's got no neutrons. It's just a positive, it's just a proton and an electron. And if you lose that electron, you're left with just a proton, which is just H plus, okay? So just to make sure you're all listening, I know you've all had a break and having some lunch or some food can sometimes make you a bit sleepy. Just to make sure you're all awake, tell me what is an ion that loses an electron? So it loses a negative charge. What does it become? Brilliant, okay, almost all answered there. Amazing, I'm so happy. Obviously, lunch has done you guys some good because you all got that absolutely correct. It becomes positive. So now we're going to talk a bit about ionic bonding, okay? So we said already that when you lose an electron, you form a positive charge, and then when you gain an electron, you become, so not in this case, when you gain an electron, so you get 1 plus, and when you gain an electron, you get a negative charge. So this is essentially what happens in ionic bonding. And ionic bonding happens between what type of structure? So metals, non-metals, or a combination of metals and non-metals. What do you think? What kind of bonding do you get with metals and So with ionic bonding. So the question is it metals only? Is it non-metals only? Or is it a combination of metals and non-metals? Well done. You're all saying the correct answer, which is metals and non-metals. Perfect. So ionic bonding forms between metals and non-metals, okay? So remember that periodic table? The metals are all on this side, and then we have that zigzag line, which is where the non-metals are here. So this is the non-metals, and these are all the metals, okay? So think, when you're having an element from this side reacting with an element from this side, always think, well, this must be an ionic bond, okay? That will help you identify the type of bonding if you're not sure, okay? So we know that the metals, so for example, the alkali metals, which is in group 1, like lithium and sodium in group 1, lose an electron, because remember they only have one electron in their outer shell because they're in group 1. And if you lose an electron, you become positively charged, okay? And similarly, the chlorine and the fluorine in group 7, they need to gain one electron. As soon as they gain an electron, they have an extra negative charge. So they form a negative ion, okay? So remember, the metal becomes positive and the non-metal becomes negative, okay? So straight away, you should be able to think, so what's going to happen if I have something positive and something negative? So they must be close enough to each other for this one to give its electron away. So as soon as it gives it away, it becomes positive, the metal, and the non-metal becomes negative. So you have these two things very close to each other, so close that they've given away electrons. So it's like they've made an exchange. So for example, giving someone something in their hand, as soon as they try to let go, what's going to happen is that they have this positive and negative charge, which always attracts, and straight away they combine, okay? So that's what an ionic bond is. So you have the metal giving away one electron to become positive, the non-metal gaining that electron, so you can see the electron here is from the sodium, and because there's now a positive charge and a negative charge so close to each other, the only thing they can do is stick together, okay? So if you think about, you have the two magnets, positive and negative, and you put them together, whatever you do, they'll try to stick together, okay? So that's what ionic bonding is. It's the electrostatic attraction between a positive and negative ion, okay? And in order for you to form that positive and negative ion, you must be giving away an electron. So exactly here. And once it comes together, so you have the positive charge here and negative charge here. And when you combine that positive charge and negative charge, the overall atom has no charge, okay? So it's a positive charge and negative charge attracted to each other to form this ionic bond. As you can see, as soon as that becomes negative and positive, they join up. But overall, there is no charge to the substance. So if you think about sodium chloride, who knows what sodium chloride is? What do we use sodium chloride for? What's another name? A household. It's a household, but it's something that you all use, I'm sure, in your cook. Exactly, salt. So if you think about salt doesn't have a charge on it, okay? Because it's an ionic bond made of sodium and chloride. The sodium had a charge, the chlorine had a charge, but coming together, that charge cancels out, okay? And that is your ionic bonding. So ionic bonding is very, very strong type of bonding. If you think about a strong magnet is what it's like, the positive and negative ions sticking together. And the way they can form a bonding is by a strong lattice. So if you can think about, see this, so this is sodium and chloride, so the purple is chlorine, the green is sodium. You can just see you've got constant repeating of the sodium and chloride. And this is, you know, this will be negative, positive, negative, positive. So this positive is attached to this negative, this negative, this negative. It's all attracting to each other. So you have forces in all directions in the lattice. So this green here is attracted to this purple, that, because they're all having to, they all have opposite charges. So you have this really, really big structure where you have a kind of a really nice arrangement of the positive and negative ions, and they are so attracted to each other that you get this strong formation where it's all attracted to each other in all directions, and it sticks together really, really nice and tightly. So that's an ionic bond. So you form, in order to get ionic bond, you form ions. Those ions then are attracted to each other because they're positive and negatively charged, and those can then attract to other ions and other ionic bonds to make a big, giant lattice. Okay, so based on that, what you know so far, what can you tell me about some of the properties of ionic substances? So what can you tell me, for example, if you have this structure, what do you think about the melting and boiling point of these structures, which are really, really strongly held together by strong electrostatic forces? So the word strong is here. So what do you think? What does it tell you about the boiling point and melting point? Is it going to be really high or is it going to be really low? Are you going to be able to easily boil and melt them, or is it going to take a lot of energy to boil and melt them? So they are very, very strong bonds. So in order to cause this to melt or to boil it to make it into a gas, you need to break these really, really strong bonds up. So that means that the boiling point is going to be what, high or low? Exactly, it's going to be very, very high, okay? So ionic bonds are very, very strong bonds, okay? That's one thing to remember, is ionic bonding is strong. Between positive and negative ions, okay? So you require a lot of energy. So if you're trying to boil this giant lattice, it's going to take a lot of heat energy to do that. So the melting point and the boiling point is very, very high, okay? So that's one thing to remember. The next thing we're going to talk about is whether or not ionic bonds can conduct electricity. What do you all think? Can they conduct electricity? So someone said yes. Anyone think no? So most people saying yes. Someone's saying no. Okay. So this is a bit of a trick question actually, because the answer is a bit of both. So ionic substances in themselves cannot conduct electricity, but if you melt them, what can happen is that they have electrons that can move around in a liquid. So when they are molten, so when you melt them, they can conduct electricity. So it was a bit of a trick question because actually the answer is yes, no, unless they are molten, okay? So this is very important to remember because they will, when they ask you about substances like this and they ask you, for example, is it conductor, is it not? The answer is only when molten, okay? So ionic bonding, so in order for you to carry electricity, you need to have electrons that can move around and carry an electric charge from A to B in a wire, for example. And if you have, for example, salt, if you think about salt, if you put, you know, electricity into salt, nothing's going to happen. But actually, if you were to melt something like the salt into a liquid and put that electricity through it, what will happen is that the electrons can move around and they can conduct electricity. So key thing to remember about ionic bonding is that they can move freely when molten, so they can conduct electricity when they are molten, okay? So it means when they're melted, essentially, okay? So when you melt them, which requires, as we saw before, a very high temperature to do that, they can conduct electricity, okay? And that's sometimes used as one of their properties. Does that make sense? So when we're talking about ionic bonding, we need to remember kind of the charges that we can get. So we know with group 1, we're always going to get a 1+ charge because they have 1 electron in the outer shell and they want to get rid of that to get a noble gas structure. We know with 2+, with the group 2 atoms, they all have 2 electrons in the outer shell and they all want 2, 8, 8. They all want to have 8. So what happens with this one is they need to lose 2 electrons to get noble gas structure. The alternative will be to gain 6 electrons, which, as you can imagine, is going to take a long time. So they'd rather lose 2. With group 3, similarly, they either need to gain 5 electrons or lose 3. It's much preferable for them to lose 3 electrons, so they get 3+. Okay, because remember they have 3 electrons in the outer shell, and they want to lose those to make them noble gas structure. Group 4 is a bit of a middle ground area. So if you can imagine, if it's got 4 and it needs to get to 8, it doesn't matter. It's the same amount of energy if they want to gain 4 or if they want to, lose 4. Okay? So either way, they'll either go down 1 shell and get to 8, or they'll go up to complete that shell to make 8. Does that make sense? Why the group 4 ones can be 4+ or 4-? Yes, okay, good. So, because they want to get to 8, they either gain 4, lose 4, doesn't make a difference. Whereas, for example, from group 3, they need to gain 5 or lose 3, and it's much easier to lose 3. And then as we get here, so these are more of the non-metals, if we think about here. So this is group 1, 2, 3, 4. This is group 5, needs to gain, this is group 6 and 7. So group 5 needs to gain 3 to make it to 8. So they always make 3-. Group 6 needs to gain 2 to make it to 8. So that makes it 2-. And group 7, as we've gone through already, needs to gain 1 to make it 8. So it's a 1-. So 1. Okay? So even if you don't know anything, you can actually calculate what the ion charges will be. It normally makes it a bit easier for you in the question, but this is how you can calculate that. Just by looking at the group number and saying, actually, it wants to go up to 8. So how can it do that? Well, actually, it's easier for it to gain 3 electrons to make it 3 minus charge. And then as I mentioned with the transition metals, the reason we don't put a number in them because they're very, very variable in what charge they can get, okay? So some of them can have more than 1 charge, so we don't put them on, but they're mostly positive because remember we said metals make positive ions, non-metals make negative ions. So you can see that from this bit here. The negative ones are on the non-metal side. So how can we write up the formula? So remember before I asked you that question with the sodium and the chloride, you guys weren't really sure which one it was. When you have ions and you want to know how many of each, so, you know, how do we know this is 2? How do we know this is 2 and this is 3? The easiest way to remember it is that when you have ionic substances, all you need to do is swap the charge number around to make the number of ions. So for this one, for example, in sodium chloride, you have 1 plus here and 1 plus here. So you don't need to do any swapping because it's the same, so you know you get that. Now, in these two, you know you have 2 plus for magnesium because it's in group 2. So if you have Mg2 plus Cl minus, what you want to do to find out, so you know it's MgCl you're getting as the final product, but you don't know the number of which. So all you need to do is you need to swap the charges. So the 2 comes here and the 1 goes here, but you don't need to write Mg1, you just write MgCl2. So you just swap the charges around, okay? Because you need 2 minus charges to make 1, to add 1 of these, okay? And that way you know now you have equal number of charges. So you know if you have a 2 plus charge, you need 2 minuses, so you need 2 of these. You can remember it that way, or the easiest way, just swap the charges. So I'll show you a more complex example. So the Al 3 plus O, oxygen is in group makes 2 minus charges. So we know it makes aluminium oxide, because you just combine them. So what we need to do is swap the charges. So for the oxygen, you get 3, and for the aluminium, you get 2. Does that make sense, everyone? So just to make sure you're all listening, we've got another poll. What do you think? Ionic bonds can conduct electricity when molten. True or false? So remember when I asked you, can ionic bonds conduct electricity, and you weren't really sure. What do you think now? Can they conduct electricity? Well done, everyone. And you all, almost all of you agreed that yes, they can. So remember, ionic bonding can conduct electricity only when molten. Okay, so we're going to talk about covalent bonds next. And covalent bonds is a little bit tricky in that they have different types of bonding within them. So as we spoke about in the beginning, with covalent bonds, they are sharing a pair of electrons, which is why they are stuck together. So with ionic bonds, they don't necessarily share the electrons. One gives away the electron, one gains the electron, and then the negative charges and positive charges form a strong electrostatic attraction. Whereas with covalent bonds, they have to stick together because they are sharing that electron. And the only way they can both have a noble gas structure, so a full outer shell, is if they are sharing those electrons. There's no giving and taking. So that's an important thing to remember. But because they are sharing them, there's nothing that you can do. So it's going to be very, very hard for you to separate those, because as soon as you separate them, they're both going to, 2 things are now going to have the structure which is not ideal, with more or less electrons than needed. So you can get 3 different types of covalent bonds. You can get small molecules. So that's like the hydrogen, the H2O that we saw before, where you just have 1 hydrogen and 2 oxygen, okay? Very, very tiny molecule there. You can get very large molecules, which I'll show you an example of, which is like glucose, which is, as you can see, it's not tiny like the water, but it's got loads and loads of bonds of carbon, hydrogen, and oxygen. And then finally, you can get to what we call the giant covalent structures, which is something like diamond, which is masses and masses of bonds held together by covalent bonds. And that's what it looks like. So tell me, what do you think with covalent bonds? Are they metals, non-metals, or combination? What do you think they tend to be? What kind of things form covalent bonds? Combination, someone said a combination of metals and non-metals. You don't think anything different? So actually, covalent bonds, as someone has mentioned correctly, tend to be made from a combination of non-metals, so two non-metals. So if you think about hydrogen, oxygen, carbon and oxygen, they're both non-metals. In fact, they're both all gases, but you can get non-gases as well. Okay, so remember, ionic bonding is metal and non-metal. Covalent bonding is non-metals, okay? So you can show them different ways how you can show a covalent bond. So the key thing to remember is that they are sharing electrons, okay? So as you can see here, the X is from one atom and the circle is from a different atom, okay? So that's one way you can identify that they're sharing electrons, and it tells you where the electron is coming from. So you know that the circle dots are coming from the nitrogen and the crosses are coming from the hydrogen. That's how you can see where are the electrons coming from. And from you can see from this one here, there are 3 electrons that are being shared. So in order for ammonia to complete its outer shell, it needs, it's in group 5, it needs 3 extra electrons, and so you can get 3 extra hydrogens. That's a nice handy way for it to get an outer shell. And the hydrogen has 1 electron in its outer shell. Remember, it's 1 proton, 1 electron. So it just needs 1 more. So that's why you need 3 hydrogens to make an outer shell with 1 nitrogen. And again, you can draw it similarly like this, just drawing the letters without the circles and showing that it's sharing electrons. So you know that these 2 are just from the nitrogen, this is from nitrogen, 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 and the crosses are coming from hydrogen. Or you can show like this to show how the bond is made. And this is something that you'll see a bit further down in our chemistry sessions. So I mentioned the giant covalent substances. So I've given one example, which is the diamond. And, you know, it's loads and loads of covalent bonds in a continuous network, similar to the ionic bonding. You know, it's very similar to that lattice we saw before. But tell me, what do you think are some examples of giant covalent substances other than diamond? So we know diamond is one. So don't know any other ones. Someone said graphite. Well done. Anything else? There's a few. So yes, so silicon. And then the last one I'm going to show you here is something called fullerene. So one thing to remember about these, they all tend to be made from carbon. Okay, these are all carbon atoms joined multiple ways to make these. Okay, so these are giant covalent substances, and that makes them a bit different to the other substances that we saw. For example, the hydrogen and the water. These are multiple bonds formed, which are very, very strong, which gives it slightly different properties. So they're very, very hard. So for example, diamond and the graphite, very, very hard substances. The graphite is like what you find in pencils. So if we just look at the way carbon is, so carbon can make, it's got 6 protons, okay? You know, that's what number. So tell me, how many electrons does carbon have? Who can tell me how many electrons do you think carbon has in the carbon atom? Perfect, 6. Okay, so going back now, so tell me how many electrons are in the outer shell of a carbon atom? So we have 2 in the first. Oh, that's not nice, very nice. So we must have 2 in the first, and we have 4 left over. So we must have 1, 2, 3, 4. Excellent, okay? So we know that straight away, carbon has 4. And remember, carbon is one in that group, in the group 4, where you can get a 4 plus or 4 minus, because they can gain or they can lose electrons to make a full outer shell. So one of the important things to know about in terms of a giant covalent structure is graphite, because graphite doesn't act like a normal covalent substance, and that's because it can conduct electricity. Okay, now if I show you what the graphite looks like, you can see this carbon atom is how many bonds is it formed with the one surrounding it. How many bonds can you see that this carbon has made? So this one on its own, so it's actually made 3 bonds. So if you see the dark lines on the bonds, so 1, 2, 3 bonds. Okay, similar. If I pick any of them, they've all made 3 bonds. So for example, this one is 1, 2, 3. This one is 1, 2, 3. Okay, so it's made 3 bonds with another carbon atom. So we know that carbon has got 1, 2, 3, 4 electrons, but only 3 of them have made bonds. So what happens to this extra electron here? What do you think happens to it? Well, the answer is actually here. It becomes delocalized, and what that means is it just floats around in the rest of the structure. Okay, so in graphite, you're only making 3 bonds with each carbon. So you have an extra electron that's not bonding to anything. And because it's not bonding to anything, it wants to say, well, it says, well, there's no point of me being here. So it floats around and becomes what we call delocalized, okay? And delocalized means it's not local to any of the atoms, okay? Just think about the word delocalized. It's not local to any of the atoms, okay? And that's why, because there's electrons floating around here everywhere, those electrons can carry a charge through the structure, and therefore it is a conductor of electricity. Does that make sense? So because you have an electron in the carbon atom that's not bonded, that electron is extra, because in graphite only, because only 3 bonds are made, and so it can become delocalized, and therefore it can conduct electricity. So it's one of the few covalent substances that can conduct electricity, and the only reason is because it's got delocalized electrons, which can carry the charge, okay? If you look at the structures here, so this carbon, for example, in diamonds, attached to 1, 2, 3, 4. This one here has got 1, 2, 3, 4. So there's no free electron in this diamond, which is why diamond doesn't conduct electricity. Whereas here you have just 3 bonds, 1, 2, and it's going down. Does that make sense, I hope? And that's all because we know that carbon must have 4 electrons in its outer shell and only 3 are bonded, okay? So having gone through that, what are some of the properties that you think of the simple covalent? So we know that those big giant covalent structures are very, very hard. Like if you think about diamonds, you know, you can't really boil and melt diamonds. It takes a lot of energy. They're very, very hard. But things like water, carbon dioxide, what can you tell me about those? Do you think they have high or low boiling and melting points? What do you think about water, high or low boiling point relative to, for example, diamond? Exactly, it's very, very low. So water, you can boil it in your kettle at home. So you know if you can do it in your house, it's not going to be that hard to break it up, okay? So they have, for example, you have the water molecules here. You may have hundreds and thousands of them. The forces between them are very weak. So these covalent bonds are quite strong, but the force between them are weak. So it's easy to break that up and make it into a gas. But for example, the giant covalent structures that we saw before, it's very, very difficult for you to break these structures up because there's so many bonds involved in them, you just can't do it, okay? So the simple molecular structures have very, very low boiling points and melting points, but the giant covalent structures have very, very high melting and boiling points. And generally, covalent bonds are very, very strong bonds because they need to share those electrons and they don't want you to separate them because then both those atoms are going to need to then find other ways to get a full outer shell. So tell me now that you've all been listening and you all understand this, how are covalent bonds formed? So far I'm reassured that your answers are all good. We'll wait for a few more of you to answer. Okay, I'm going to end it there. Well done. So again, correct. So 2 atoms sharing electrons. So tell me, what do you think it is when we say, what is A? What is this describing? Electrostatic attraction between positive and negative ions. What is that? Exactly, that is an ionic bond. So already, if we have the word, it makes it easy for you. So things are simple. You have ions, they form ionic bonds, okay? 2 elements mixed together without any chemical reaction. This is a mixture. And 2 atoms sharing electrons is your answer for covalent bonds. This does not even exist. You will not be able to share protons because they're in the nucleus, okay? So metallic bonding. So who can tell me anything about metallic bonding? Some of the properties, anything about them, what can you tell me? You've already got the nice little diagram here which tells you what metallic bonding is, but what can you tell me about metallic bonding? They're strong, excellent, so strong. So if you think about metals around you, they're definitely strong. You have these freely moving negative electrons. Straight away, what does that tell you? We talked about it with graphite. If you have something that can move around, and what can it do? Conductors, perfect. So they conduct electricity and heat. Someone said malleable, excellent. So that means you were listening when I was talking to you before about the difference between metals and non-metals, okay? The answer all the same. So the key things to remember, so metals consist of a giant lattice of atoms, which are positive, and they're very, very regularly arranged. If you look here, they're all in nice little rows, okay? So you have the positive ions, the electrons are delocalized. What that means, if you have a metal, the electrons are all separated from the main ion, the main atom, and just float around freely. But because you have all that positive charge and negative charge, they're all held together. Because even though they're moving away from the actual atom, it's attracted to all of the other positive ions there. So the electrons are free to move, which gives it a very nice property of being able to conduct heat and electricity. But it also means that the positive charges are also held very closely together, and that makes them very, very strong bonds, okay? So there's a very, very strong attraction between those positive nucleus and the delocalized electrons. Even though the electrons are able to move, they're still making sure they're all held together. So someone said malleable and that you can move them. So that's true. Now, if you imagine they're all in these nice little rows, but what that means is that these rows can easily slide over each other, okay? So as you can see, if you move this, these little balls slide over the ones underneath, okay? And that gives it some of its properties. So that means they can be hammered into shape. So remember we said that metals are also ductile in that they can be used to form things like pipes and, you know, different shapes. You know, when you have metals, you can make metals into rings and jewelry. And that's really because they have these layers which you can move into shape. So that's really important property. We already know that metallic bonding is strong, and we already know that strong bonds have high melting and boiling points, because if you have a very strong bond, it requires a lot of energy and therefore a higher temperature to break those bonds apart and melt them and condense them. Does that all make sense? Great. The other thing about metallic bonds is sometimes you can form alloys. Does anyone know what alloy is? And there's an example of an alloy here. What's an alloy? Or anyone know an example of any alloys? I know if you're into cars, you'd be thinking about like alloy wheels and stuff. So use that to think of your answer. Perfect. So someone said steel, which is exactly the answer. So someone said aluminium. So aluminium is actually an element, okay? But you can use aluminium to make alloys. So the definition of alloys is a mixture of elements, specifically metals with other elements, usually other metals. So for example, steel is not an element. Steel is made from iron and other metals to make it stronger and give it specific properties. You also, when you sometimes have gold jewelry, it's not pure gold. So you may hear, for example, gold plated, or like gold mixed with some silver, or gold mixed with something like other metals, just to make it, you know, bigger and, you know, that a little bit cheaper sometimes as well. So alloys also have metallic structure, but some of the atoms are different sizes. So for example, if you have iron mixed with a bit of copper, the iron atom is different size to the copper atom. So you don't get these nice little lines like we do here. And that's the point, because you don't want to be able to bend it. If you think you have a big building made up of the steel frame, you don't want it to be able to bend and, you know, someone to hammer into shape. So you may make it out of steel, which then makes it harder. And this is how it does that. So if you think about, this is a classic, just pure metal element. And these are examples of alloys where you have other metals combined. And now because of this distortion of shape here that you see here, this bit is not easily going to slide over like it was in this section here. So alloys just make it more difficult for the layers to slide over each other, and that helps to maintain its structure. I hope that makes sense in terms of what alloys are. Alloys are basically just metals mixed with other metals. Okay, so it's more than one metal put together. So similar to a mixture, but it does make them stronger. So just before we have another little quick break, just to go over the different types of bonding. So remember we said ionic bondings are oppositely charged ions attracted to each other because of a negative and positive charge. Covalent bonding is when you have atoms sharing electrons, and metallic bonding is positive metal ion in a sea of delocalized electrons. And normally ionic bonds is between metal and non-metal, covalent is non-metals, and metallic is just pure metals. Okay, so that should help you remember. You have one for metal and non-metal, 1 for non-metal, and 1 for metal. I hope that all is a bit quite clear. So we're just going to go through some questions that you might get asked in an exam. So we will start with this one here. The first thing I want to ask is, in which group, so just look at the picture and the answer should be given to you. Which group of the periodic table is fluorine in? So I'm going to just tell you, you have 2 electrons here, and you have 1, 2, 3, 4, 5, 6, 7. Perfect. So it's in group 7, and someone's even written halogens. Perfect. So just to make sure we all know about the halogens, I want you to tell me, with the halogens, now remember that they need to gain an electron. How does the reactivity change as you go down the halogens from fluorine, from fluorine to chlorine to bromine to iodine? How does the reactivity change as you go down? Are they more or less reactive? Okay, this is making sure you're recapping what we're going through. As we go down, bearing in mind they need to gain an electron. Perfect. So I'm so glad you remember this, because this is very important, that they become less reactive as you go down, because they get bigger and bigger, and this positive charge in the middle, which is where the nucleus is further away from the electron, so less likely to be attracted. Well done, guys. Okay, so this is similar to what we've just gone through now. So use information and your knowledge of graphite, which we've just gone through, so hopefully it's fresh in your mind, to answer the question. So it tells you here, scientists have made a new substance called graphene. The bonding and structure of graphene is similar to graphite. So you can see graphene is a single layer of the atoms of graphite. The bonds between atoms in graphene are, who knows, what must they be if it's similar to graphite? So we have ionic, covalent, metallic. So graphite, remember, is what we call a giant structure, but is it covalent, metallic, or ionic? I'm getting a few mixed answers here, but I'm glad overall majority, so it is actually a covalent bond, okay? So remember, graphite is one example of a giant covalent structure, okay? So it's covalent. And other examples, we have our diamond, fullerene, and silicon. So graphite is made up of carbon, okay? So it doesn't tell you that here, but you have to know that. So you see that it doesn't tell you all the information, but it's a covalent bond. It's one example of a giant covalent structure. And just adding on to that, who can tell me what is the special property of graphite that's different to every other covalent bond that we've done? What's the special property of graphite? Perfect, it conducts electricity, and that's because it's got delocalized electrons, okay? Very, very important that you remember that as well, because it's an important property, and this is how they ask you in your exam. So we know what graphite is made up of. So what is graphene made up of? Chromium, carbon, or chlorine? It's a bit tricky because they've put C for all of them. So what do you think? Well done, you all know it's carbon, okay? And that's why it makes normally 4 bonds. Here it's only made 3 bonds, and now you get an extra electron. And that's actually answered the question. Each atom is bonded to how many other atoms? So if you just pick one of these here, you have 1, 2, 3. So you can look at the picture and answer this question, or if you know from memory, actually, I remember in graphite, you have 3 atoms bonded to other atoms. That will give you the answer. Okay. We're going to go on a break now, and then when you come back, we've got a bit more exam questions, but I don't want to kind of bombard you too much now. So we'll come back at around 3:30 for the last half an hour, which will be just pure exam practice. So take a break now. We'll see you back shortly at 1:30. Hello, welcome back everyone. I hope you had a nice little break. So the last part, we're going to be going through loads of exam questions, and then we have a quiz at the end, which I know you all enjoy doing. So we'll just continue with these questions for now, and then we'll do the quiz. So there's another question, which is actually a 4-mark question. So remember, when there's 4 marks, you need to give 4 different points. So I want you to give me 1 point if you can, 2 if you're feeling a bit more brave. Why do metals conduct electricity? So what do we think? Why do metals conduct electricity? And think about the structure of metals and metallic bonding, which can enable it to do this. So why do metals conduct electricity? So perfect. So someone said delocalized electrons. So what does that mean? What does that mean? So what can delocalized electrons do? Because someone said there's a giant lattice. Because if you have, for example, just 2 bonds, you're not going to be able to conduct electricity. Giant structure of bonds or atoms. They have delocalized electrons. Someone said the electrons can carry a charge. And in order to carry a charge from A through the structure to B, those electrons have to be able to move freely, okay? So through the whole structure, they have to be able to go from this end to that end freely. So when the question asks you why do metals conduct electricity, write down the most obvious thing you can think of, as opposed, in addition to what the specific reason is. So yes, we know delocalized electrons, but actually that on its own doesn't give us the answer. The answer is that those delocalized electrons can freely move and carry a charge through this large structure of atoms. Okay, so if you look at what the answer was, so you need to know that they have a giant structure of atoms, they have delocalized electrons, which are free to move through the whole structure. And they can carry a charge. So this is how you get 4 marks. So very, very simple. And they do accept variations of this. So, you know, are free to move, can carry a charge, all these things will give you an option. And someone's actually written a perfectly written answer out for me as well. So well done. So delocalized electrons are free to move throughout the structure and so can conduct electricity because electrons can carry a charge. Perfect, 4 marks for that kind of question. I hope that all makes sense and how you can explain that, okay? So the most important thing to remember is with metallic bonding, you have those positive charges and those electrons are delocalized and free to move and carry that charge across. So this diagram below represents an electron structure of the oxygen atom. Okay, so atoms, remember, have no charges. So how many electrons do we see? So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in total. And 1, 2, 3, 4, 5, 6 in the outer shell. Okay, so firstly, what group is oxygen in? Just by what we've seen today, what group is oxygen in? It must be in group 6. Perfect, because it's got 6 electrons. So the oxide ion, so the ion oxygen makes, remember, it needs to get to 8, which is 2 more electrons, is O2 minus, okay? So what does that look like here? So how many electrons am I drawing around this structure? How many electrons? 8. So I'm going to continue drawing the 6 that we had already. So we get 2 extra electrons. And you can see now we have 8, which is the noble gas structure. So we have 2 and 8. And we have 2 extra electrons. So we have 2 extra negative charges. So it's 2 minus. Okay, nice and simple. So they accept dots, crosses. They don't need to be paired. And they don't need to allow electrons in the first shell. Okay, so you can't add any electrons here. Anything you add here will be incorrect. Okay, it needs to be in the outer shell because remember the first shell can only have 2 electrons. Okay, so what I want you to do now is have a look at this one, and you just need to do the word equation. Okay, so you need to get things right. So you're trying to make sodium fluoride. So what's the word equation for this? What are you adding to sodium to make sodium fluoride? And you have to get the spelling right in these ones, and that's the main thing. It's all in that question. Exactly. It's honestly giving you the correct answer here. So this is a very simple question. So sodium plus fluorine becomes sodium fluoride. But the thing is, so substances in which atoms of two or more different elements are chemically combined are called what? So what do we call it when these two things come together to form the sodium fluoride? What is the name of this? What do you guys think? Perfect. Compounds. So things that are chemically combined are called compounds, okay? Simple as, very, very straightforward. Doesn't require much thought. Okay. So this is a bit of a more wordy question again. So this is talking about different type of bonding. So figure 2 shows what happens to electrons in the outer shell when sodium reacts with the fluoride. So you see the first part is building up to this part. The dots and crosses represent electrons. Okay, so here you have 1 electron, and here you have 7 electrons. Okay, so describe as fully as you can, so they want details here, what happens when sodium reacts with fluorine to produce sodium fluoride. So what I want you to do in the chat is type out the answer that you'd give. I'll just check how many marks this would be. So this is actually a 4-mark question. So you need to give 4 points for this question to answer this and get the maximum amount of marks. So tell me, what 4 things would you write in your answer for this question? Okay. I'll wait for a few of you to answer and then we'll go through it. Good, so we're getting a few answers. So sodium loses, and you have to specify the number of electrons to get the mark for this one, okay? So it loses 1 electron. That's 1 mark. Fluorine gains 1 electron. That's 2 mark. So then tell me what happens. You forming a positive ion and a negative ion. And that's what happens to produce sodium fluoride that attract. Okay, this will give you the maximum marks. Now I'll show you what the mark scheme shows and you can see how simple this question is. So sodium atom loses 1 electron, fluorine atom gains 1 electron. Okay, so that's already 3 marks just by saying that you're losing and gaining electrons. Okay, and this forms ions. You can also say, as some of you had said, to get a full outer shell to form an noble gas structure. Okay, and also writing ionic bond will give you a mark. Writing positive or negative ions will give you a mark. So you see, it's very, very simple. You need to write exactly what's happening. It's very, very straightforward. As long as you know what's happening, what's losing electrons, what's gaining it, but always write the number of electrons being lost and gained because it can differ for different elements, okay? So now my colleague is going to we're going to do a quiz. So we're just going to ask Ace to share her screen so we can put the quiz up for the last 10-15 minutes. Whenever you're ready, she'll share her screen. I'll just stop sharing mine. Let's give it a few seconds. And I'm loving the answer you guys are sending me for that last question. Really good. So I know you all know how to use the Kahoot. So if you can just, we're going to give you the code. Okay, so you just need to get the pin. If you just go in Kahoot on Google or on your phones, and then just enter this pin where it says enter game pin. You can put your name as whatever you want. It doesn't necessarily need to be your own name, just something that will help you identify yourself. And once you join, we will get started. Good, we've got some bondings joining. Well done. A few more of you to join. So 6684394. We have 60, I think one or two more of you left. Almost done. Wait, one more person joining. Let's message someone. If anyone hasn't been able to join, just message me in the chat. Otherwise, we're going to start it now in a few minutes, maybe in a minute or two. Oh, brilliant. There you go. Okay, I think we'll, okay, let's start now. We'll start now. Okay, I will read the question out for you guys just in case someone isn't as quick as reading for the next ones. You do have a set time limit for these though. Well done, Crispy Bacon. Which of these are covalent bonding? AlCl3, NH3, NAF, H2O. Remember what covalent bonding is and what kind of things are combined using covalent bonds. Which of these is covalent bond? You have 2 seconds left. Well done, it's H2O and then H3. Covalent bonding involves electron transfer, sharing, exchange, or movement. What is a covalent bond, remember? Well done, I'm glad to miss you got that. Electron sharing. Transfer is an ionic bond. Okay. Ionic bonding is sharing of electrons or transfer of electrons. Well done, I'm glad to see that you all got that one. All within the time as well. Transfer of electrons. Covalent bonds are bonds between metal and metal, metal and non-metal, or two non-metals. Good. Bit of a combination. Remember, covalent bonds tend to be non-metal and non-metal. If you think about carbon dioxide and water, it's H2O, they're both non-metals. Look at the pictures there, you see they're both non-metals. What happens to electrons during ionic bonding? Are they shared, transferred, delocalized, or nothing? It's about the protons. I'm looking forward to seeing. Well done, they are transferred. So remember, protons do not get shared, transferred, nothing happens to protons. Well done, Asim. We have. What combination of elements is used in ionic bonding? Remember, ionic bonding, and look at the picture to help you. Is it metals only, non-metals only, metal and non-metal, or any? Well done, metals or non-metals. Remember, sodium is an alkali metal. Chlorine is a halogen, which is a non-metal. It's right at the end of the periodic table. What other elements in group 1? Are they non-metals, metals, halogens, or salts? Group 1. Perfect. Remember, they're called alkali metals, so that will help you remember what they are. What is the most reactive metal in group 1? Fancy, remember, more reactive as you go down, because the more likely to lose an electron because it's further away from the positive proton nucleus. That was a tough one. Group 1 elements. Do they have a full shell of electrons, have one electron missing from the outer shell, one electron in the outer shell, or different number of electrons in the outer shells? What do we know about group 1 elements? Perfect, they all have one electron in the outer shell. Remember, group 1 has one electron, group 2 has 2 electrons. Group 7 elements form ions with a charge of what? Group 7. Well done, -1. Remember, they need to gain 1 electron to get a full outer shell because they've got 7 already, and they need 8. And our final question, group 7 elements are called group 7, remember, alkaline earth metals, transition metals, halogens, or noble gases. Well done, most of you got that as the halogens. The noble gases are group 0, which are right at the end. Well done, so we can see, I think, Stephanie, well done, 3rd place. Lily, well done, excellent. And Asim, you did very well. Very high score with just 1 question wrong. I think all 3 of you actually only got 1 question wrong. It just Asim was a bit faster. So well done, everyone. Actually, really good. And I'm glad to see that actually you hopefully have learned something. Please do fill in the feedback form that's on the chat, just so we can help. So when you come to our next sessions, it's even better. Tell us what you liked. Do you like the quizzes? Do you not like the quizzes? Do you think we had too many questions or not enough? And was the detail enough? Was it too fast? So all very important for us and also for you. But thank you so much. If you do have any questions, now's the time to ask. So we're going to go through if you have any questions or anything you weren't sure about. Otherwise, we will see you next month in our next lesson. So we will hang about here for a bit. I think I have. So those who, oh, thank you for everyone saying thank you. Really appreciate that you were listening here on a Sunday for so long, and it was quite a lot of talking. You all did very well. You all knew a lot more, I think, than I was anticipating with all the answers you were giving me. Everyone was very, very on the ball and knowing everything, and excellent answers to the exam. Someone actually asked me to make the exam questions harder. If you all agree with that, then I think I will do for the next session, make them a little bit trickier, a little bit harder questions. Or some people saying no. I think we'll put a mix in, I think, just to make it a bit more balanced. Because I think the question I'm asking is what you will get in your normal exam. So I'll only put actual real exam questions in there. But I will try to add a few more higher level to help you guys as well and test you a bit more. But yeah, if you don't have any further questions, I'm happy for you to, I think you all did very well. You all knew a lot of information, and I'm hoping that you've learned quite a bit. So please do fill in the feedback, and then you're ready, whenever you're ready, feel free to head off and enjoy the rest of your Sunday.